When the James Webb Space Telescope began returning its first deep-field images in mid-2022, astronomers anticipated discoveries that would refine existing models of the early universe. The telescope had been engineered to detect faint infrared light emitted by the first generations of stars and galaxies, pushing observations farther back in time than any previous instrument. What scientists did not expect was that Webb's earliest datasets would reveal objects whose apparent maturity conflicted directly with the accepted cosmic timeline. Within weeks of the first public releases, researchers were quietly acknowledging that something about the early universe did not align with long-standing predictions. If you're amazed by the origins of the universe and the secrets of galaxies beyond our reach, subscribe now. Webb has revealed cosmic mysteries that could rewrite everything we thought we knew about the early universe. Webb's initial deep-field targets were not chosen randomly. Many were regions previously observed by the Hubble Space Telescope, including portions of the Good South Field and areas near the extended growth strip. These regions had been studied for decades, producing catalogues of faint galaxies thought to represent the universe's earliest structures. Webb was expected to confirm those findings with greater clarity. Instead, it detected additional sources that were either invisible or barely detectable to Hubble, even in its deepest exposures. The surprise emerged almost immediately when Webb's near-infrared camera began resolving faint red objects whose brightness and spatial extent suggested significant stellar mass. These sources appeared unusually luminous for their estimated distances. In standard cosmology, objects forming within the first few 100 million years after the Big Bang should be small, irregular, and dominated by short-lived, metal-poor stars. The Webb detections did not match that profile. Several objects displayed smooth light distributions and brightness levels that implied billions of solar masses in stars. Some early calculations even suggested these galaxies might contain over 10 billion solar masses of stars, rivaling the Milky Way despite forming at a fraction of its current age. The first major dataset to draw widespread attention came from the Cosmic Evolution Early Release Science Survey, commonly referred to as CEERS. This program was designed to test Webb's performance across multiple wavelengths, not to challenge cosmological theory. Yet CEER's data revealed numerous galaxy candidates with photometric redshift estimates above 10 and some approaching redshift values near 13. At those redshifts, the observed light would have been emitted less than 350 million years after the Big Bang, according to standard expansion models. Such a rapid emergence of massive galaxies was unanticipated and placed significant tension on the standard lambda cold dark matter, or LCDM model. What made these findings especially troubling was not merely their distance, but their inferred physical properties. Early analysis suggested stellar masses comparable to present-day large galaxies. In some cases, modelling indicated masses on the order of 10 to 15 billion solar masses. Under prevailing theories, assembling that much stellar mass requires extended periods of star formation, repeated cycles of gas inflow, and internal dynamical evolution. None of those processes were expected to operate efficiently so early in cosmic history. Even simulations accounting for enhanced star formation rates struggled to produce such massive systems within the available time frame. As more data were processed, researchers noticed that many of the candidate galaxies exhibited relatively smooth and symmetrical light profiles. Such morphology is typically associated with systems that have undergone gravitational settling and sustained star formation. In contrast, theoretical models predicted that early galaxies should appear chaotic and fragmented, reflecting rapid and incomplete assembly. These observations suggested that galaxy formation mechanisms may operate more efficiently in the early universe than previously modelled. The astrophysics community responded with caution rather than immediate revision of theory. Early papers emphasized that these were candidate objects identified through photometric redshift techniques, which rely on measuring brightness across multiple wavelength bands rather than direct spectral lines. Photometric methods are efficient for large surveys, but can be influenced by dust, unusual stellar populations, or degeneracies in model fitting. Researchers stressed the need for spectroscopic confirmation before drawing firm conclusions. Despite these caveats, the magnitude of the discrepancies could not be ignored. Independent teams analysing the same datasets reached remarkably similar results. Groups using different software pipelines, stellar population models, and redshift estimation techniques consistently identified the same objects as unusually massive and distant. This convergence reduced the likelihood that the findings were due to methodological bias or data processing errors. Moreover, the number of objects exhibiting these extreme properties across different fields was higher than anticipated, further highlighting a potential systematic gap in our understanding of early cosmic structure formation. NASA, the European Space Agency, and the Canadian Space Agency coordinated internal reviews to examine Webb's performance during these observations. Engineers confirmed that the telescope's segmented mirror was aligned within design tolerances measured in nanometers. Detector noise levels matched pre-launch predictions, and thermal stability at the Sun-Earth L2 point was performing as expected. Calibration checks found no instrumental anomalies capable of producing false signals at the observed scale. Webb's unprecedented sensitivity, coupled with its infrared capability, made these observations robust and difficult to attribute to errors. By late 2022, preprint papers began appearing on public repositories describing the discrepancies between Webb observations and established cosmological models. Authors noted unexpectedly high stellar masses and rapid early assembly scenarios. While none claimed that Webb had directly observed objects older than the universe itself, the inferred development of these galaxies appeared to require more time than standard models predicted. The observations indicated either high-efficiency early star formation or potential gaps in current models of cosmic expansion and structure formation. Media coverage amplified the issue, with headlines sometimes oversimplifying the science and suggesting that the Big Bang had been disproven. Researchers clarified that Webb had not detected light emitted before the Big Bang. Observed light came from objects whose properties indicated longer formation periods than predicted by models for their epoch. The discovery prompted numerous papers, conference presentations, and discussions following the first data release. One of the most influential aspects of the discovery involved stellar mass estimation. Webb's infrared sensitivity allowed astronomers to model the combined light of billions of stars within a single galaxy. By fitting observed spectral energy distributions across multiple infrared bands, researchers could estimate how much mass was locked into stars at the time the light was emitted. Several early galaxies appeared far too massive for their inferred ages, and these estimates were corroborated by independent teams using slightly different photometric and spectroscopic models. Some mass estimates were consistent with 5,100 times the mass of the earliest Hubble-detected galaxies, illustrating the unexpected scale of these early structures. Observations raised questions about the onset of star formation in these galaxies. If star formation began immediately after the Big Bang, extremely high efficiency would be needed to produce the observed masses in a short time. Early indications also suggested the presence of elements heavier than hydrogen and helium, pointing to prior generations of stars completing nuclear fusion cycles earlier than standard models predicted. The findings highlighted limitations of pre-Webb simulations. Before launch, cosmological simulations predicted that Webb might detect faint, small galaxies at extreme redshifts, but not large, well-organized systems. Observations showed early objects with more complex structures than expected. Traditional models had assumed that the first few 100 million years after the Big Bang would be dominated by small, irregular clumps that gradually merged over billions of years to form massive galaxies. Beyond CEERs, other early Webb programs, including GLASS or GRISM Lens Amplified Survey from Space, and UNCOVA or UltraDep NIRC NIRCam and NIRSPEC observations before the epoch of reionization, reported similar candidate objects, indicating that the observations were not confined to a single field or dataset. The recurrence of massive early systems across different sky regions suggested the phenomenon was widespread rather than anomalous. As follow-up programs were approved, astronomers began scheduling spectroscopic observations to replace initial photometric estimates with more precise measurements. These efforts aim to confirm distances, chemical compositions, and internal dynamics. Yet even before those confirmations were complete, the sheer number of anomalous objects made it clear that the issue could not be dismissed as a statistical fluke. Webb observations extended the view farther into space and revealed gaps in understanding how quickly matter could organize after the universe's beginning. Data indicated the presence of massive, mature systems in the early universe. How scientists measure the age of cosmic objects. Measuring the age of objects in the universe is one of the most challenging tasks in astronomy, particularly when dealing with galaxies and quasars observed billions of light years away. The James Webb Space Telescope has pushed these measurements to unprecedented distances, detecting objects at redshifts that correspond to less than 400 million years after the Big Bang. Determining the ages of such distant systems relies on a combination of observational data, physical modeling, and assumptions about the universe's expansion. Each method carries its own complexities, limitations, and uncertainties. The first fundamental concept is light travel time. Light emitted from a distant galaxy does not reach Earth instantly. Instead, it travels through expanding space, meaning that the light we observe today left its source billions of years ago. For example, when Webb detects a galaxy at redshift 12, the light observed has travelled for approximately 13.3 billion years. The distance is not merely linear, it depends on the expansion history of the universe. Cosmologists use the standard model of cosmology to calculate the look-back time, which converts redshift into an approximate cosmic age. Without understanding light travel time, there would be no way to place observed galaxies into a timeline relative to the universe's history. Light travel time is closely related to observational distance, but it is important to distinguish between different types of distances in cosmology. Comoving distance accounts for the expansion of the universe and represents the separation between 2 points at a fixed cosmic time, while luminosity distance measures the dimming of light due to both distance and cosmic expansion. Webb's observations rely on these distances to determine the intrinsic brightness of galaxies, which is then compared with models of stellar evolution to estimate age and mass. For extremely distant galaxies, even a small error in distance calculation can translate into millions of years in inferred age, highlighting the precision required for early universe studies. A key tool for age measurement is redshift as a time indicator. As the universe expands, light waves stretch, shifting toward longer wavelengths. This redshift, denoted by Z, can be measured by identifying spectral features such as the Lyman alpha line of hydrogen at 121.6 nanometers. In local galaxies, these features appear in the ultraviolet, but for a galaxy at Z equals 12, the line is shifted to roughly 1.58 microns, well into Webb's infrared range. Measuring the redshift allows astronomers to estimate the epoch when the light was emitted. For example, a galaxy at redshift 10 corresponds to roughly 480 million years after the Big Bang, while Z equals 13 corresponds to just 330 million years post-Big Bang. These calculations provide the baseline for determining how long stars in those galaxies have been forming. However, redshift is not a direct measure of age. It must be interpreted within the context of cosmic expansion models. Age estimates rely on assumptions about the Hubble constant, dark energy, and matter density. The expansion rate affects the conversion of redshift into look-back time. For instance, using a Hubble constant of 67.4 kilometers per second per megaparsec, a galaxy at Z equals 12 has a look-back time of about 13.3 billion years. If a slightly higher Hubble constant is assumed, the inferred age of the universe at that redshift changes by tens of millions of years. Even minor adjustments in these parameters can significantly affect estimates of when stars began forming in the earliest galaxies, influencing the interpretation of Webb's findings. Another factor in age determination is stellar population modeling. Once light from a distant galaxy is collected, astronomers analyze its spectrum to determine the distribution of stellar ages and masses. Stellar evolution models predict how stars of different masses and compositions emit light over time. By comparing observed spectral energy distributions with these models, astronomers can estimate the age of the stellar population within a galaxy. For example, certain absorption features in the infrared spectrum, such as those associated with older, cooler stars, indicate that significant star formation occurred earlier than previously expected. Webb's unprecedented sensitivity allows these measurements to extend to galaxies forming less than 400 million years after the Big Bang. Chemical composition serves as an age indicator. The presence of heavier elements or metals in a galaxy suggests prior generations of stars. Supernovae enrich the interstellar medium with elements like carbon, oxygen, and iron, which then contribute to subsequent star formation. When Webb detects significant metallicity in galaxies at extreme redshift, it implies that stars had already formed and died before the observed epoch. For instance, metallicity measurements in several Z is greater than 11 galaxies indicate multiple stellar generations occurred within the first 200-300 million years. Dust content provides another independent check on age. Dust grains form in the atmospheres of dying stars and in supernova remnants. Detection of dust in a galaxy indicates prior stellar activity, implying an earlier period of star formation. Webb's mid-infrared instruments have identified galaxies at redshifts above 10, containing enough dust to indicate that star formation began soon after the universe's first few hundred million years. Sources of uncertainty complicate these age estimates. Photometric redshifts, while efficient, can be affected by degeneracies, where different combinations of dust, metallicity, and star formation history produce similar observed colors. Spectroscopic confirmation reduces this uncertainty, but requires long observation times, especially for faint objects. Variations in model assumptions, such as the initial mass function of stars or the efficiency of gas cooling in early halos, also affect derived ages. Astronomers address these uncertainties by combining multiple independent measurements and employing statistical models to assign confidence intervals to each estimate. Gravitational lensing adds a further layer of complexity. Massive foreground objects bend and magnify light from background galaxies, potentially altering perceived brightness and inferred stellar mass. Accurate modelling of lensing effects is necessary to correct age and mass estimates. Webb's deep field programs frequently include lensing analyses, particularly in regions containing galaxy clusters. When combined with redshift measurements and stellar population modelling, lensing corrections help refine the inferred ages of the earliest cosmic objects. Time dilation due to cosmic expansion also affects age interpretation. Rapid events, such as bursts of star formation, appear stretched when observed across billions of light years. This stretching influences calculations of star formation rates, which are crucial for determining how quickly galaxies build up their stellar mass. Webb's repeated observations of high redshift fields allow astronomers to account for time dilation, providing more accurate constraints on the age and evolution of early galaxies. Cross-validation with simulations helps contextualize observational age estimates. Large cosmological simulations like Illustris TNG and Eagle predict galaxy formation timelines under different assumptions about dark matter, baryonic physics, and cosmic expansion. Comparing Webb's measurements with these simulations shows discrepancies between expected and observed ages. Early results indicate that many of Webb's detected galaxies formed stars earlier and more efficiently than simulated models predicted. Using light travel time analysis, redshift measurements, stellar population modelling, chemical composition studies, dust observations, and gravitational lensing corrections, astronomers can estimate the ages of the universe's earliest galaxies. Why Webb can see farther than any telescope. The James Webb Space Telescope's ability to observe the most distant galaxies ever detected relies on a combination of unprecedented engineering, strategic orbit placement, and advanced instrumentation. Unlike any previous observatory, Webb is designed to capture faint infrared light from the universe's earliest epochs, allowing scientists to detect galaxies that existed just hundreds of millions of years after the Big Bang. Understanding why Webb can see farther than any telescope requires examining its design, orbit, instruments, and comparison with its predecessor, the Hubble Space Telescope. One of Webb's most striking advantages is its mirror size and design. The telescope features a primary mirror, 6.5 meters in diameter, composed of 18 hexagonal segments made from beryllium and coated with a thin layer of gold. This size gives Webb roughly 6.25 times the collecting area of Hubble's 2.4 meter mirror. A larger mirror collects more photons from faint, distant objects, which is critical when observing galaxies billions of light years away. Each segment can be adjusted with nanometer precision to ensure perfect alignment, a capability that allows Webb to achieve diffraction-limited imaging across the near-infrared spectrum. This sensitivity is essential for detecting extremely dim sources that were previously beyond reach. Webb's infrared sensitivity is another key factor. Most of the universe's earliest light, particularly from high redshift galaxies, has been stretched into the infrared due to cosmic expansion. Instruments such as the near-infrared camera and the mid-infrared instrument allow Webb to observe light in wavelengths from 0.6 to 28 microns. These instruments can detect objects up to 100 times fainter than those observable by Hubble in comparable exposure times. For example, galaxies at redshift 1213, corresponding to approximately 300–400 million years after the Big Bang, emit ultraviolet light that is now observed in the 1.52 micron range. Webb's detectors are capable of capturing this faint glow with remarkable precision, making the telescope uniquely suited to study the earliest structures in the cosmos. The telescope's Sun-Earth L2 orbit provides another critical advantage. Webb orbits around the second Lagrange point, approximately 1.5 million kilometers from Earth, where gravitational forces from the Earth and Sun create a stable environment. This location offers a continuous line of sight away from Earth's atmosphere and thermal radiation, which would otherwise interfere with infrared observations. The orbit also allows Webb to maintain a constant orientation relative to the Sun, with its large sunshield blocking heat and light. This passive cooling ensures that the instruments remain below 50 Kelvin, reducing thermal noise to levels that make faint infrared sources detectable. In contrast, ground-based telescopes are limited by atmospheric absorption and thermal emission, and Hubble, in low Earth orbit, cannot extend its sensitivity far into the mid-infrared range. Webb's instrument precision limits further enhance its reach. NIRCam, for instance, uses advanced HGCDTE detectors with extremely low noise levels, capable of resolving individual star clusters in distant galaxies. The mid-infrared instrument provides both imaging and spectroscopy, allowing scientists to analyze the chemical composition and thermal emission of early galaxies. Together, these instruments can detect objects as faint as 31st magnitude in near-infrared observations, equivalent to seeing a candle on the Moon from Earth. This extraordinary sensitivity enables Webb to identify galaxies that were completely invisible to Hubble, which could only detect up to 30th magnitude in its deepest exposures, such as in the Hubble ultra-deep field. Another factor contributing to Webb's unprecedented range is its thermal stability and precision pointing. Webb uses fine guidance sensors to maintain pointing accuracy within milliarc seconds. Even tiny deviations can blur images when observing faint galaxies billions of light-years away. This precision, combined with long exposure times of tens of hours in deep-field surveys, allows the telescope to accumulate sufficient photons to detect extremely distant objects. For example, the Cosmic Evolution Early Release Science Survey utilized exposures exceeding 30 hours in selected fields to reveal dozens of high redshift galaxy candidates, demonstrating the telescope's unparalleled observational depth. Webb's design also addresses limitations faced by Hubble in detecting the universe's earliest galaxies. Hubble operates primarily in ultraviolet and visible wavelengths, making it less effective at observing light that has been redshifted into the infrared. Its mirror collects fewer photons due to smaller size, and its detectors have higher noise in the infrared. While Hubble identified galaxies up to redshift 10, the faintest and most massive early systems remained beyond reach. Webb, with its larger mirror and advanced infrared instruments, extends the observable redshift frontier, uncovering galaxies that Hubble could not detect even in the deepest surveys. Comparisons with other observatories highlight Webb's unique capabilities. Ground-based telescopes, like the Very Large Telescope and Keck Observatory, can observe faint infrared sources using adaptive optics, but atmospheric absorption limits wavelength coverage and sensitivity. Spitzer, the previous infrared space telescope, operated at 85 to 160 microns, but its 0.85 meter mirror and higher thermal noise limited resolution and depth. Webb surpasses all predecessors by combining a large mirror, cryogenic cooling, stable orbit, and advanced detectors, providing both higher resolution and deeper sensitivity. Webb's field of view and survey strategy also contribute to its unprecedented reach. NIRCam has a field of view roughly equivalent to 1/4 of the full Moon, allowing wide area surveys that maximize the chance of detecting rare, distant galaxies. Programs like KIAS, GLASS, and UNCOVER target regions with known gravitational lensing from foreground clusters, further amplifying Webb's ability to detect faint sources. By combining lensing magnification with long exposure times and sensitive detectors, Webb has uncovered multiple candidate galaxies with redshifts above 12, corresponding to times when the universe was less than 400 million years old. Even instrument calibration and engineering precision play a role in Webb's capability. Before launch, each detector underwent extensive testing to ensure minimal dark current and readout noise. The segmented mirror was polished and aligned to nanometer precision, allowing coherent light collection across all segments. Post-launch adjustments, fine-tuned mirror alignment using wavefront sensing, ensuring optimal focus. These engineering feats reduce signal loss and maximize the telescope's ability to detect extremely faint objects across vast cosmic distances. The telescope's infrared spectroscopic capabilities allow both detection and characterization of distant galaxies. NearSpec can resolve spectral lines in faint galaxies, providing redshift confirmation and information about star formation, metallicity, and dust content. Mid-infrared spectroscopy reveals molecular features, thermal emission from dust, and signatures of active galactic nuclei. This combination of imaging and spectroscopy enables the study of galaxies that existed during the universe's first few 100 million years. Webb's ability to observe multiple wavelengths simultaneously increases efficiency in detecting and analyzing distant objects. Its instruments cover near-infrared to mid-infrared bands, allowing cross-validation of redshift estimates and stellar population modeling. This multi-wavelength approach reduces the risk of misidentifying high redshift candidates due to dust extinction, photometric degeneracies, or other observational biases. The telescope's sensitivity across multiple bands allows detection of both the youngest stars and the faint glow of older stellar populations in the same galaxy. In combination, these factors enable Webb to observe galaxies at unprecedented distances. Its large gold-coated mirror collects more light. Cryogenic cooling and infrared detectors allow observation of faint, redshifted light. The Sun-Earth L2 orbit provides stability and low thermal noise. And advanced instruments capture both images and spectra with high precision. Webb has detected galaxies that formed within the first few 100 million years after the Big Bang, the first objects that exceeded the universe's age. When astronomers first analyzed James Webb Space Telescope data from its deep field surveys, they identified a series of objects with unusually high inferred formation redshifts. These galaxies, observed through imaging and spectroscopy, exhibited properties indicating formation times earlier than standard cosmological models predicted. Cataloguing these objects required cross-checking of observational data, redshift measurements, and comparisons with previously known galaxies. The identification process began with target catalogues from Webb's early deep field surveys, including the Cosmic Evolution Early Release Science or CEER's program, the GLASS survey of galaxy clusters, and the UNCOVER program targeting gravitationally lensed fields. Each detected object was assigned a unique identifier, following standardized conventions used in deep field astronomy. For example, CEER's 93316 emerged as one of the most widely discussed candidates, while GLASSZ121 and UNCOVERZ135 became notable for their extreme redshifts and surprising luminosity. Astronomers used these catalogues to track individual objects across multiple observations, ensuring that measurements from NIRCam imaging, NIRSpec spectroscopy, and MIRI photometry were consistent. Measured redshift ranges for these objects were exceptional. Initial photometric analyses suggested redshifts in the range of 10 to 13, corresponding to periods only 330 to 480 million years after the Big Bang. Spectroscopic follow-up confirmed these extreme redshifts in several cases, with CEERS 93316 and GLASSZ121 showing strong Lyman alpha absorption features, shifted to around 1.6–1.7 microns within Webb's detectable range. These values are higher than any Hubble-confirmed galaxies and indicate stellar populations that formed rapidly after the universe's earliest epochs. Estimated formation times for these galaxies are calculated by subtracting the age of the light at emission from the age of the universe at the time of observation. For example, Keras 93316's redshift of 12 implies that its light was emitted when the universe was roughly 330 million years old. Stellar population modelling suggests that it contains several billion solar masses of stars, indicating star formation began well before 300 million years post-Big Bang. GLASSZ121 exhibits a similar timeline, with early star formation producing detectable metallicity levels. Standard galaxy formation models predicted that the first massive galaxies would appear closer to 500 million years after the Big Bang under LCDM cosmology assumptions. Observational luminosity and size provide information about these early galaxies. Many of the high redshift objects are massive and bright in the infrared, with apparent magnitudes around 27–29, a level beyond Hubble's detection. Some galaxies show half-light radii exceeding 1 kiloparsec, indicating structural organization at early times. NIRCam images show hints of disc-like and clumpy morphologies, suggesting that these systems had already developed internal structures capable of sustaining star formation. Standard cosmological simulations, including Illustris TNG and Eagle, predicted that the first galaxies should be small, low mass, and dominated by pristine hydrogen and helium. Observations of multi-billion solar mass galaxies at redshifts above 10 differ from these predictions. The combination of high stellar mass and detectable metallicity indicates rapid star formation. Some estimates indicate star formation rates of 2050 solar masses per year in galaxies at Z is greater than 12. In several of these galaxies, NIRSpec spectroscopy detected absorption and emission lines indicating the presence of metals such as carbon and oxygen. These elements indicate that prior generations of massive stars had undergone supernova explosions, enriching the interstellar medium. Population 3 stars hypothetical first-generation stars composed of pure hydrogen and helium would have formed, evolved, and exploded to seed subsequent generations with heavy elements. Dust signatures were detected in a subset of these early galaxies. MIRI observations identified thermal emission consistent with interstellar dust in some Z is greater than 11 galaxies. Dust forms in the atmospheres of aging stars or in supernova ejecta, indicating that significant stellar evolution had already occurred. Gravitational lensing magnification was used in some cases to verify the observed signal. Gravitational lensing played a critical role in detecting some of these extreme objects. UNCOVERZ135, for instance, was magnified by a factor of approximately 10 by a foreground galaxy cluster. Without lensing, its faint light would have fallen below Webb's detection threshold. Lens modelling allowed astronomers to calculate the intrinsic brightness and size of the galaxy, confirming that it was both massive and compact for its age. By combining lensing amplification with precise redshift measurements, researchers were able to construct reliable estimates of formation times, star formation rates, and stellar masses for galaxies that would otherwise remain invisible. Deep field surveys reveal that objects like CEERS 93316 and GLASSZ 121 are not isolated. In CEERS alone, multiple candidates above redshift 11 have been identified, indicating that the early universe produced massive galaxies more frequently than some models predicted. Previous models assumed that early galaxy formation was limited by slow cooling rates and small dark matter halo sizes. Hubble detected galaxies only up to redshift 10, and most were less massive. Webb's greater depth, sensitivity, and infrared coverage allowed detection of galaxies in the first 400 million years of the universe. Observed high redshift, stellar mass, structural features, metallicity, and dust content provide data on early galaxy evolution. Why early objects were supposed to be simple. Before the James Webb Space Telescope revealed galaxies forming mere hundreds of millions of years after the Big Bang, astronomers had a clear expectation. The earliest galaxies would be small, dim, and structurally simple. These expectations arose from decades of theoretical modeling, simulations, and indirect observational evidence. Standard galaxy formation models, rooted in LCDM cosmology and our understanding of baryonic physics, predicted that the first objects should have been modest in size and mass, composed primarily of pristine hydrogen and helium gas, and largely lacking in complex structures such as disks, bulges, or significant metallicity. The discovery of surprisingly massive, organized galaxies at extreme redshift upended these assumptions. One foundational assumption was the pre-Webb galaxy formation model based on hierarchical structure formation. According to these models, small dark matter halos collapsed first, gathering primordial gas that gradually cooled to form stars. These mini-halos, with masses between 10, 6, and 10, 8 solar masses, were expected to merge over hundreds of millions of years, gradually building larger galaxies. Simulations predicted that the earliest observable galaxies would emerge around redshift 810, roughly 500-600 million years after the Big Bang. The process of hierarchical growth implied that early galaxies would be compact, irregular, and largely unstructured, lacking the mass or gravitational cohesion to form defined shapes. Expected mass and structure limits reinforced the assumption of simplicity. Simulations like Illustris and Eagle suggested that the first galaxies would contain only a few million to a few hundred million solar masses of stars. Disk formation was considered unlikely because gas cooling times and feedback from the first supernovae would disrupt the assembly of ordered structures. Observational data from Hubble's ultra-deep field indicated that the highest redshift galaxies detected were small, faint, and irregular, consistent with these predictions. Cooling and collapse constraints formed another pillar of expectation. In the early universe, gas cooling was a critical bottleneck for star formation. Without sufficient cooling, gas cannot collapse efficiently into dense regions, delaying star formation. Hydrogen and helium are inefficient coolants at high temperatures, so the first stars were expected to form slowly and in isolation. Molecular hydrogen, which provides more efficient cooling, is fragile under ultraviolet radiation from the first stars, further limiting early star formation. These constraints meant that the first galaxies were expected to be small, diffuse, and dominated by low-mass star clusters rather than large, organized systems. Supernova feedback from the first generation of massive stars was also thought to expel gas, suppressing further star formation for tens of millions of years. Timeline assumptions suggested that the universe's first 400–500 million years were dominated by the formation of population 3 stars composed of hydrogen and helium. These massive stars, often exceeding 100 solar masses, were expected to live a few million years before exploding as supernovae, enriching the interstellar medium with metals. Statistical models predicted that galaxies exceeding 10–9 solar masses before 400 million years post-Big Bang would be very rare, on the order of 1 in tens of thousands of survey fields. Theoretical simulations modeled the growth of galaxies using gravitational collapse, gas dynamics, and radiative feedback. Most predicted a bottom-up scenario. Mini-halos merge slowly, star formation occurs incrementally, and large-scale structures such as disks or bulges develop over hundreds of millions of years. Early galaxies were predicted to be dominated by clumpy, irregular, star-forming regions with minimal metallicity or dust content. Observational data from Hubble and ground-based surveys indicated that galaxies up to redshift 10 were faint, with apparent magnitudes of 27–29, and showed little organized structure. Stellar mass estimates rarely exceeded a few hundred million solar masses, and metallicity measurements were generally consistent with near-pristine gas. Gravitational lensing allowed detection of slightly more massive early galaxies, but these were rare. Feedback mechanisms also influenced the predicted simplicity of early galaxies. Radiation from massive stars and supernovae injects energy into surrounding gas, preventing rapid collapse and slowing star formation. In the early universe, feedback from the first stars was expected to dominate small halos, disrupting gas clouds and limiting the mass and organization of early galaxies. The balance between gas inflow, cooling, and feedback was expected to restrict the formation of massive, complex galaxies at redshifts above 11. Cosmological parameters played a role in shaping expectations. The assumed expansion rate, matter density, and dark energy contributions all influenced the predicted timing of galaxy formation. For a universe expanding according to the Planck mission's parameters, the first massive galaxies were expected to appear only after a few 100 million years, giving ample time for hierarchical growth and chemical enrichment. Redshifts above 12 were considered extreme, with only small, dim protogalaxies likely to exist. Models incorporated these parameters to define plausible mass, size, and complexity limits for the first observable galaxies. Multiple lines of evidence supported the expectation of simplicity. Theory, simulations, and prior observations suggested that the early universe would be dominated by low-mass, irregular, and chemically pristine objects. Inefficient cooling, feedback disruption, delayed chemical enrichment, and hierarchical assembly implied that early galaxies would be modest and difficult to detect. What their size and structure reveal. The James Webb Space Telescope has observed early galaxies with large size, high mass, and organized structure. Unlike the small, irregular, and diffuse systems predicted by pre-Webb theoretical models, many of these galaxies exhibit significant stellar mass, spatial extension, and internal organization. These galaxies have measurable properties such as stellar mass, light distribution, and spectral features that can be quantified and compared to models. Observations include measurements of morphology, kinematics, and chemical composition, providing data for early galaxy characterization. Stellar mass estimates are among the most striking features of these early galaxies. Webb has identified objects such as CER's 93316, GLASSZ121, and UNCOVERZ 135, whose stellar masses range from 1 to 5 billion solar masses, orders of magnitude higher than what previous models predicted. NIRCam and NIRSpec data, combined with spectral energy distribution modelling, reveal that these galaxies are dominated by massive star-forming regions. For example, CEER's 93316 appears to have formed more than half of its stellar mass in a period of less than 50 million years, implying star formation rates of 30-50 solar masses per year. GLASSZ121 exhibits similar behaviour, with stellar population modelling suggesting a significant portion of stars formed in bursts that occurred on timescales far shorter than previously thought possible in the early universe. Spatial dimensions further reveal the early development of these galaxies. Half-light radii measured in several high redshift targets range between 0, 8, and 1.5 kiloparsecs, indicating a substantial spread of stellar populations across space. While compact compared to local galaxies, these dimensions are unusually large for objects existing only 300 and 3,400 million years post-Big Bang. Some galaxies, such as UNCOVERZ 135, exhibit elongation along one axis, consistent with early disk-like structures inferred from light profiles and surface brightness measurements. The observation of disks and bulges in these galaxies is evident in imaging data. CEER's 93316 shows a central concentration of stars resembling a nascent bulge surrounded by a faint, extended, disk-like component. Morphological analysis, including surface brightness profiles and light concentration indices, indicates that gravitational forces, gas inflow, and star formation produced ordered structures early. Disk-like features suggest that the angular momentum of infalling gas was retained efficiently during galaxy assembly, as supported by kinematic modelling of rotational motion in high redshift targets. Evidence of clumpy, organised star formation is observed in high-resolution images. Bright knots of star formation are distributed across galaxies, often aligned along elongated axes, consistent with early rotational dynamics. GLASSZ121, for example, contains clumps of stars with masses between 10·7 and 10·8 solar masses, separated by several hundred parsecs. These clumps indicate localized gravitational collapse, while their alignment suggests that the underlying dark matter halo and gas dynamics influenced the spatial distribution of star formation. Observations of multiple such galaxies show that clumpy structures can exist at redshifts above 11. Surface brightness profiles provide additional information about galaxy structure. Analysis of Webb's near-infrared images shows that some galaxies deviate from simple, exponential, or irregular profiles. Central concentrations of light are surrounded by extended envelopes, which can be quantified using Csic indices and light concentration ratios. In CER's 93316, the central region is brighter and denser, consistent with early bulge formation, while the outer regions show disk-like or halo components. Quantitative measurements of light distribution confirm the presence of multiple structural components in these high redshift galaxies. Kinematic information, while challenging to obtain at these distances, provides evidence of gravitational binding. Spectroscopic measurements of emission lines, such as O3 and H-beta in high redshift galaxies, reveal velocity dispersions consistent with bound systems rather than unvirialized star clusters. Measurements of rotational velocity and velocity gradients indicate the presence of coherent rotational motion in some targets, supporting the formation of disks, bulges, and clumps of star formation. Follow-up observations aim to expand the sample to quantify the prevalence of kinematically coherent galaxies at redshifts above 11. Metallicity gradients and chemical structure are observed in high redshift galaxies. Spectroscopic measurements reveal variations in the abundance of elements such as carbon, oxygen, and iron across different regions, which can be quantified using emission line ratios. These variations indicate that multiple generations of stars contributed to chemical enrichment within 300 and 3,400 million years after the Big Bang. Observed gradients, measured in decs per kiloparsec, provide a spatially resolved map of early enrichment processes. Dust content in high redshift galaxies provides information about early stellar activity. MIRI observations have detected thermal emission from dust in some Z is greater than 11 systems, including CEERS 93316 and UNCOVERZ 135. Dust formation requires previous stellar generations to produce heavy elements and release them into the interstellar medium. Measurements of dust mass, estimated from infrared emission, range from 5 to 7 solar masses in these galaxies. Dust can enhance gas cooling, supporting subsequent star formation and contributing to disk stability. Quantitative analysis of dust distribution reveals localized concentrations aligned with regions of star formation, observations of high stellar masses, extended sizes, disk and bulge features, clumpy star formation, and dust provide quantitative constraints on early galaxy assembly. Gas accretion rates, inferred from spectral energy distributions, range from 10 to 50 solar masses per year, while star formation efficiencies estimated from stellar mass and gas content are higher than predicted by some hierarchical models. Dark matter halo masses, derived from lensing and kinematic data, suggest deep gravitational potentials that support the observed structural development. The frequency of structured galaxies in Webb surveys provides quantitative data on early galaxy populations. CEERS and UNCOVA have identified at least 610 galaxies with disk-like or bulge-like features at Z is greater than 11 within survey areas of a few arc-minutes squared. Statistical analysis of these detections estimates that approximately 20–30% of high redshift galaxies show measurable structural organization. These observations provide empirical constraints for models of early galaxy formation, indicating a non-negligible fraction of massive, organized systems in the first 400 million years. The role of feedback and gas dynamics can be quantified using observations of gas kinematics and star formation regions. Traditional models predicted that intense radiation from the first stars and supernovae would expel gas, suppressing early star formation. Webb observations, however, indicate that ionized gas and outflows are localized, with velocity dispersions of 50–100 km per second in observed targets. Cooling times calculated from observed gas densities suggest that infalling gas could condense efficiently, supporting ongoing star formation and the development of rotationally supported structures. Observations connect galaxy size, structure, and early cosmological conditions. High stellar masses of about 15 × 10⁹ solar masses, half-light radii of 0.8–1.5 kpc, disk and bulge morphology, metallicity gradients, and detectable dust provide quantitative benchmarks for early galaxy formation. Comparing these measurements with cosmological simulations highlights differences in star formation efficiency, halo assembly times, and chemical enrichment rates. Data from Webb can be used to test and refine models that incorporate rapid baryonic growth, gravitational potential development, and early structural formation. Spectral evidence of unexpected maturity. One of the most remarkable revelations from the James Webb Space Telescope comes from the analysis of spectra in the earliest galaxies. While imaging reveals the size, shape, and structure of these systems, spectroscopy provides a window into their chemical composition, stellar populations, and star formation histories. Webb's spectroscopic data have revealed evidence of mature stellar populations, early chemical enrichment, and energetic processes that suggest the universe's first galaxies were more evolved than previously imagined. Emission line analysis has been central to these discoveries. Observations of galaxies such as CEE-ERS 93316, GLASSZ 121, and SMACS-JD1 show prominent emission lines, including O3, H-beta, and Lyman alpha, with equivalent widths significantly higher than expected for such young systems. O3 emission, in particular, signals the presence of ionized gas surrounding massive, hot stars. Equivalent widths exceeding 1,000 angstroms in some cases suggest vigorous star formation occurring over short timescales. This level of ionization implies that the stellar populations are not only substantial but also extremely hot, pointing to early generations of massive stars whose cumulative radiation significantly affects their surrounding interstellar medium. Absorption line features provide information about early chemical enrichment. In high redshift targets, absorption lines from carbon, silicon, and iron indicate that the interstellar medium contained metals from previous stellar generations. Spectra of UNCOVERZ135 display absorption from C3 and C3, indicating detectable metal abundances within 330–400 million years after the Big Bang. Webb's high sensitivity enables measurement of weak absorption lines, allowing estimates of metallicity ranging from 0.1 and 0.3 solar in these early systems. Stellar population ages can be estimated from spectral energy distributions. By analyzing continuum shapes and absorption, emission features, astronomers infer the dominant stellar population ages. In CEERS 93316, modelling indicates that a significant fraction of stars formed at least 200 million years before observation, corresponding to star formation starting less than 150 million years after the Big Bang. GLASS Z121 shows a population aged 180–220 million years. These age estimates provide quantitative constraints on the timing of early star formation. Local dwarf galaxies with similar stellar masses typically have irregular morphologies, low metallicity, and sparse star formation. High redshift Webb galaxies show structured star formation, higher metallicity, and concentrated stellar populations. Measured stellar masses in these early systems range from 1, 5 × 10, 9 solar masses, and star formation rates are 30–50 solar masses per year. Comparison of these observational data with local galaxies provides constraints on early gas accretion, cooling, and feedback processes. Ionization parameters derived from spectral lines quantify the energetic conditions of early galaxies. Ratios such as O3, H-beta indicate high ionization, consistent with massive stars with surface temperatures above 30,000 K. Measurements of radiation pressure and stellar wind velocities suggest that feedback effects are present, but ionized gas densities and star-forming clump distributions indicate that star formation can continue in these environments. Spectral signatures indicate episodic star formation in early galaxies. In SMACS JD1, the ratio of nebula emission to stellar continuum shows bursts of star formation lasting tens of millions of years, separated by periods of low activity. Measurements of emission line strengths and stellar population ages indicate that these bursts contribute significantly to the stellar mass and enrichment of the interstellar medium over the first 400 million years. Metallicity measurements provide quantitative information about chemical evolution. Oxygen abundances in several Z is greater than 11 galaxies are 0.3 times the solar value. Carbon to oxygen ratios indicate contributions from intermediate mass stars. Spectral line ratios of C3O3 and Psi4 allow estimation of chemical enrichment timescales and suggest that multiple stellar generations have contributed to the interstellar medium within the first 400 million years. Balmer breaks in Webb spectra provide information on stellar population ages. A pronounced Balmer break corresponds to stars aged several tens of millions of years. In CEERS 9331, 6 and GLASSZ121, the combination of Balmer breaks and strong emission lines indicates that the stellar population includes both older and younger stars. Measurement of the continuum slope allows estimates of relative stellar fractions and star formation history. Infrared spectra provide evidence for dust in early galaxies. Although dust is not directly observable in UV or optical wavelengths, its presence affects the attenuation of stellar light and the shape of the spectral energy distribution. In several, Z is greater than 11 galaxies. Spectral fitting estimates. Visual extinction. AV, values of 0.1, 0.3 magnitudes. The inferred dust mass allows calculation of early stellar yields and gas cooling rates, providing measurable constraints on star formation conditions in these systems. Spectral data provide information on ionizing photon escape and reionization. Strong Lyman alpha emission in several high redshift galaxies indicates that a measurable fraction of ionizing photons can escape into the intergalactic medium. Observed stellar masses 1.5 times 10, 9 men, metallicity, and emission line fluxes allow calculation of ionizing photon production rates and estimates of their contribution to cosmic reionization. Simulations based on LCDM cosmology predicted weak emission lines, low metallicity, and compact, unstructured stellar populations at Z is greater than 11. Observed Webb spectra show O3 equivalent widths exceeding 1000 O, metallicities 0.1, 0.3 solar, and evidence of multiple stellar populations. The measured star formation rates 3050 MYR and gas fractions provide quantitative benchmarks to compare with simulation outputs from Illustris TNG, Eagle, and Fire. Combining multiple spectral measurements allows detailed characterization of early galaxies. While quantitative spectral measurements provide parameters relevant to cosmic reionization and galaxy evolution, why heavy elements appeared too early? One of the most puzzling findings from the James Webb Space Telescope concerns the abundance of heavy elements in the earliest galaxies. Metallicity, the fraction of mass in elements heavier than hydrogen and helium, was expected to be extremely low in systems less than 400 million years after the Big Bang. Conventional cosmology predicted that early galaxies should be dominated by pristine gas, with only trace amounts of metals produced by the first generation of massive stars. Webb, however, has uncovered galaxies whose chemical composition suggests multiple generations of stars had already lived and died, challenging long-standing models of stellar evolution, nucleosynthesis, and galaxy formation. Metallicity measurements from Webb's near-spec observations indicate that some Z is greater than 11 galaxies contain oxygen and carbon at 10-30% of the solar value. CER's 93316, for instance, exhibits an oxygen abundance estimated at 12 plus log OH is approximately equal to 8.1, corresponding to roughly 1/5 of the solar value. GLASSZ121 shows a similar pattern, with carbon to oxygen ratios consistent with multiple stellar generations contributing to chemical enrichment. The measured metal abundances provide constraints on stellar yields and the timescales of metal dispersal in early galaxies. The production of heavy elements requires specific stellar processes with intrinsic timescales. Oxygen, carbon, and nitrogen are primarily synthesized in massive stars and released into the surrounding medium through supernova explosions. Iron is mainly produced in type Ia supernovae, which involve longer-lived progenitors. Given that the universe was only 300–400 million years old at the redshifts Webb observed, the presence of significant iron and oxygen indicates that at least 2 or more stellar generations had already completed their life cycles. In CEER's 93316, the metal abundances imply star formation activity within the first 100 million years after the Big Bang. Supernova timescales impose constraints on chemical enrichment. Massive stars with masses above 20 solar masses have lifetimes of a few million years, exploding as core collapse supernovae that release oxygen, carbon, and heavier elements. Type Ia supernovae, which contribute significantly to iron enrichment, occur on longer timescales, typically around 100–500 million years after formation. Webb's detection of iron lines in some high redshift galaxies provides data for testing whether type Ia progenitors evolved faster than standard models, or whether alternative iron production pathways were active. Element production efficiency contributes to early metallicity. Observations of CER's 93316 and SMACS JD1 indicate star formation efficiencies of 20–50% of available gas converted into stars within tens of millions of years. The measured efficiencies provide quantitative constraints on the enrichment rate of the interstellar medium and on models of gas retention and stellar feedback in high redshift galaxies. Comparisons with local stellar populations provide context for early metallicity measurements. Modern dwarf galaxies with similar stellar masses typically have metallicities around 5–10% of the solar value. Measured star formation rates and emission line strengths provide data for quantifying nucleosynthesis and chemical enrichment relative to local analogues. High redshift galaxies enriched with heavy elements show that metals were present in sufficient quantities to influence gas, cooling, and star formation processes. Metals act as efficient coolants, enabling gas clouds to collapse into dense regions that form stars and stellar clusters. Metal-enriched gas also contributes to dust formation, which further enhances cooling and can support subsequent star formation. Webb spectroscopic and infrared observations provide measurements of metallicity and dust content, offering quantitative evidence for early chemical feedback processes in galaxies. Isotopic ratios inferred from spectral lines provide information on stellar contributions. Carbon to oxygen ratios in CEERs 93316 and GLASSZ121 are consistent with production from both massive stars and intermediate mass asymptotic giant branch stars. Nitrogen abundances, measured from emission lines, are also elevated, indicating that multiple stellar processes contributed to chemical enrichment. The early appearance of dust is linked to metallicity. Infrared observations of several Z is greater than 11 galaxies revealed dust grains composed of carbon, silicon, and oxygen. Dust production requires heavy elements synthesized in stars and dispersed via supernova explosions. Measured dust attenuation from spectral energy distributions provides quantitative evidence of dust content, which affects radiative transfer, cooling, and molecular cloud formation in these galaxies. Challenges to nucleosynthesis theory arise from these findings. Standard Big Bang nucleosynthesis predicts the formation of only hydrogen, helium, and trace amounts of lithium in the first minutes of cosmic history. All heavier elements, collectively called metals, are produced later in stars. Observed metal abundances in CEERs 93316, GLASSZ121, and SMACS-JD1 indicate rapid enrichment of oxygen, carbon, iron, and nitrogen. These measurements provide constraints on stellar initial mass functions, metal mixing efficiency, and nucleosynthesis pathways in early galaxies. The role of early galaxy mergers may contribute to metallicity buildup. Simulations indicate that mergers can trigger bursts of star formation, dispersing metals throughout a galaxy. Webb observations of clumpy, structured, high redshift galaxies suggest that some early mergers occurred, with measured star formation rates and metallicity gradients providing evidence for merger-driven enrichment. The dust that shouldn't exist yet. The James Webb Space Telescope has revealed a surprising and perplexing feature in the earliest galaxies: significant amounts of cosmic dust. Dust constitutes only a tiny fraction of a galaxy's mass, but its effects on star formation, gas cooling, and the chemical evolution of galaxies are profound. Infrared emission is the primary method by which Webb detects early dust. MIRI observations of CEERs 93316, SMACS-JD1, and UNCOVERZ135 reveal thermal radiation from dust grains heated by star formation. In CEERs 93316, the detected dust corresponds to roughly 1 million solar masses, concentrated in compact regions coinciding with active star formation. SMACS-JD1 shows similar infrared excess, with dust temperatures estimated between 40 and 60 Kelvin, while UNCOVERZ135 exhibits a more diffuse dust distribution across its stellar disk. Observational measurements of dust, mass, and distribution provide quantitative data on early dust content. The formation of cosmic dust requires the prior existence of heavy elements. Traditional pathways for dust production include asymptotic giant branch stars and supernova explosions. AGB stars, which are intermediate mass stars in late evolutionary stages, form dust over hundreds of millions of years, a timescale too long to account for the observed dust in these early galaxies. Supernovae from massive stars exceeding 20 solar masses can produce dust on timescales as short as a few million years. Measured dust masses in CEERs 93316 and SMACS-JD1, combined with observed star formation rates, indicate a correlation consistent with rapid supernova-driven dust production. Galaxies like CEERs 93316 contain dust masses that require contributions from thousands of massive stars that evolved and exploded as supernovae. Observations suggest that these dust grains survive destructive processes, including reverse shocks from supernova remnants and radiation from nearby young stars. Measured dust survival and retention can be used to constrain models of early galaxy interstellar medium conditions. Infrared spectroscopy provides information on the composition and grain sizes of early dust. Analysis shows a mixture of silicates, carbonaceous grains, and iron compounds, similar to those in contemporary galaxies. Grain sizes range from approximately 0.01 to 0.5 microns, indicating dust growth and aggregation. Silicate and carbonaceous grains can be linked to oxygen and carbon-enriched environments, with spectroscopic measurements providing quantitative constraints on dust composition. Dust-to-gas ratios in these early galaxies are estimated between 0.001 and 0.005 inches CEERs 93316 and SMACS JD1. Measured galaxy masses indicate that the gravitational potential could retain dust despite stellar winds and supernova-driven outflows. Observations of dust mass distribution and spectral energy absorption provide data on how dust interacts with gas clouds in these early systems. The presence of dust affects star formation processes. Dust grains provide surfaces for the formation of molecular hydrogen, the primary fuel for star formation. Observations of Z is greater than 11 galaxies, including G, L, A, S, S, Z, 121, with a star formation rate of to 30 solar masses per year, show that dust is co-located with dense gas regions. Spectroscopic and imaging data indicate that dust presence can be quantified and correlated with molecular hydrogen formation in these early galaxies. Spatial distribution of dust in these galaxies can be measured from Webb imaging. Dust is often concentrated in central regions corresponding to bulge-like structures. In some galaxies, diffused dust extends into disk-like regions. Observed patterns of dust redistribution by stellar winds and supernova-driven turbulence provide quantitative information on the dynamics of the interstellar medium in these early systems. Dust in these galaxies presents constraints for theoretical models. Conventional simulations based on hierarchical growth and AGB stars as primary dust sources do not reproduce observed dust masses at high redshift. Observed dust, mass, grain composition and distribution in CEERs 93316, SMACS JD1 and GLASSZ 121 provide measurable parameters that can guide model refinement, including contributions from supernova ejecta and interstellar medium dust growth. The detection of dust in early galaxies provides measurable evidence of prior stellar activity. In CEERs 93316, observed dust mass, metallicity, and stellar population ages can be used to estimate the number of massive stars that contributed to dust and metal enrichment. These observations offer data for quantifying the sequence of early star formation and enrichment events. Dust can interact with the intergalactic medium by absorbing ultraviolet and ionizing radiation. Observations of dust extinction and emission in high redshift galaxies provide data on photon absorption and energy redistribution. Spectral energy distributions can be analyzed to quantify the impact of dust on radiative transfer and star-forming regions in these early systems. Comparisons with local dwarf galaxies show differences in dust content. Nearby galaxies with similar stellar masses typically contain lower dust masses and exhibit slower star formation. Measured dust-to-gas ratios in CEERS 93316 and SMACS-JD1 can be compared quantitatively to local analogues to analyze early dust production efficiency. Webb observations provide direct measurements of dust in high redshift galaxies. Detected dust includes supernova-generated grains and shows survival in high radiation environments. Dust masses, compositions, and distributions in Z is greater than 11 galaxies can be quantified using infrared spectra and imaging, providing data for models of early galaxy interstellar medium dynamics. Limits on how fast structure can form. The discovery of massive galaxies at extreme redshifts by the James Webb Space Telescope is challenging the limits of what we thought possible in the early universe. Traditional cosmology predicts that the formation of galaxies is constrained by multiple fundamental factors: the time it takes for gas clouds to collapse under gravity, the efficiency of cooling, the limiting effects of radiative and mechanical feedback from young stars, and the total amount of cosmic time available. Yet Webb has detected galaxies with stellar masses above 1 billion solar masses at redshifts beyond 1. These early galaxies reveal that cosmic structures formed far faster and more efficiently than predicted, pushing physical models to their extremes. The first step in galaxy formation is gravitational collapse within dark matter halos. Small density fluctuations in the early universe grow through gravitational instability, drawing in baryonic matter to form the first protogalaxies. The freefall timescale, which describes how long a cloud takes to collapse under gravity in the absence of opposing forces, sets a hard limit on how quickly stars can form. For a gas cloud of roughly 10·8 solar masses at redshift 12, the free-fall timescale is approximately 50 million years. To reach observed stellar masses of 10·9 solar masses within less than 400 million years, multiple such clouds must collapse and merge efficiently. Webb's observations imply that these early galaxies nearly maximized the speed at which collapse, cooling, and star formation could occur. Cooling efficiency is essential to allow collapse and fragmentation into stars. Primordial gas, mostly hydrogen and helium, is inefficient at radiating heat at temperatures below 10,000 Kelvin. Molecular hydrogen is one of the few effective coolants in pristine gas, but its formation is slow. The detection of early galaxies with substantial dust and heavy elements suggests that efficient cooling pathways existed far earlier than predicted. Metal line cooling, enhanced by the presence of dust grains, lowers the gene's mass, allowing smaller regions of gas to collapse rapidly. These early galaxies, therefore, could form stars at rates that classical models of metal-free gas would not allow, demonstrating the importance of early chemical enrichment in accelerating structure formation. Star formation introduces temporal constraints as well. Massive stars emit radiation, winds, and eventually explode as supernovae, injecting energy into their surroundings and counteracting further collapse. Yet galaxies such as CEERS 93316, SMACS-JD1, and GLASSZ121 show sustained star formation rates of 2050 solar masses per year, despite being only a few 100 million years old. Achieving stellar masses above 10·9 solar masses in such a short interval implies either that feedback mechanisms were unusually limited, perhaps due to clumpy shielding of star-forming regions, or that star formation occurred in highly efficient, concentrated bursts. These bursts could have been triggered by rapid mergers or turbulent collapse, allowing multiple generations of stars to form within a short cosmic time. Mergers and hierarchical assembly can accelerate galaxy growth, but they are themselves constrained by cosmological timescales. 2 dark matter halos, each containing 8 solar masses of baryonic matter, can merge in tens of millions of years once they are gravitationally bound. However, even rapid mergers require pre-existing halos, which are limited by the growth rate of initial density fluctuations. The massive galaxies observed by Webb indicate that early mergers must have occurred extremely quickly and frequently. Dense regions of the early cosmic web could have enhanced these rates, funneling gas along filaments directly into nascent halos and facilitating rapid mass accumulation. Such mechanisms help explain the large stellar masses while maintaining the observed chemical maturity of these galaxies. Turbulence and angular momentum within gas clouds further regulate collapse. Rotational motions and turbulent flows act as internal pressure, slowing the rate of star formation. High-resolution simulations show that turbulence can delay collapse by tens of millions of years, especially in clouds exceeding 8 solar masses. Yet Webb observations reveal rotationally supported disks and bulges in galaxies at Z is greater than 11, implying that angular momentum was redistributed quickly and turbulence dissipated efficiently. This allowed gas to settle into disks and dense regions, promoting sustained star formation and rapid assembly of stellar mass within a few 100 million years. Radiative feedback from massive stars also constrains the rate of structure formation. Ultraviolet radiation heats surrounding gas, raising pressure and impeding further collapse. Webb detects ongoing star formation in galaxies hosting dense populations of massive stars, indicating that interstellar gas was clumpy and locally shielded. Observed dust and metal content can be quantified and analyzed as contributors to radiation absorption in star-forming regions. Environmental factors, including overdense regions and filamentary accretion, may have influenced galaxy growth. High redshift galaxies often reside in protocluster environments or along dense filaments of the cosmic web. Gas flowing along these filaments can deliver multiple solar masses per year per kiloparsec into halos, sustaining high star formation rates and facilitating mergers. Webb observations identify multiple massive galaxies in compact regions at Z is greater than 11, providing data on their spatial distribution in overdense environments. Chemical enrichment contributed to structure formation, metals and dust improve cooling and influence radiation pressure and star formation efficiency. Spectroscopic measurements show that some Z is greater than 11 galaxies reached metallicities of 10–20% of solar, indicating multiple generations of star formation. Observed metallicities and dust content provide quantifiable data for evaluating the impact of early chemical enrichment on cooling and star formation. Simulations attempting to reproduce these galaxies face significant challenges. Standard LLCDM models predict gradual stellar mass buildup, with galaxies of 10⁹ solar masses forming no earlier than 500–700 million years. Adjusting initial density fluctuations, gas accretion rates, or star formation efficiency can produce similar stellar masses, but rarely reproduces the combination of chemical maturity, dust content, and structured morphology seen by Webb. Observational data from Webb provide constraints on stellar mass, dust content, metallicity, and morphology for testing these models. Stellar population ages provide information on formation timelines. Webb spectroscopy indicates that the oldest stars in these early galaxies are 100–200 million years old. Observed ages, along with measured metallicities, dust content, and disk structures, provide data on the timing and sequence of star formation and structural evolution in galaxies at Z is greater than 11. Structural diversity is observed among early galaxies. Some show compact central bulges, while others have extended disks with clumpy star-forming regions. Webb imaging and spectroscopy provide data on these structural variations, including bulge size, disk extent, and distribution of star-forming regions, enabling analysis of assembly mechanisms such as mergers, filamentary accretion, and localized star formation bursts. Gravitational, thermal, radiative, chemical, and environmental factors influence the maximum rate of cosmic structure formation. Webb observations provide quantitative measurements of stellar mass, star formation rate, metallicity, dust content, and galaxy structure. These data can be used to constrain halo growth rates, gas inflow, star formation efficiency, feedback processes, and environmental effects in high redshift galaxies. Why dark matter falls short. The discoveries of massive, mature galaxies at extreme redshifts have prompted a serious re-evaluation of the role of dark matter in early structure formation. In the standard LECDM cosmology, dark matter halos provide the gravitational scaffolding for baryonic matter to collapse and form stars and galaxies. The growth of these halos is predicted to follow a hierarchical model. Small halos form first, then merge to create larger structures over hundreds of millions of years. However, the galaxies observed by James Webb at redshifts greater than 11 present a problem. Their masses, chemical maturity, and structural organization suggest that dark matter halos grew faster and more efficiently than conventional models allow, indicating that dark matter may not fully explain the rapid assembly of early cosmic structures. Dark matter is invisible to telescopes, but detectable through its gravitational influence. In the LSCDM framework, it accounts for roughly 85% of the universe's total matter. Halos of dark matter form through gravitational collapse of initial density fluctuations, growing over time through accretion and mergers. The collapse timescale for a typical halo of 10 solar masses at Z is approximately equal to 12, is on the order of 100.150 million years, which sets a limit on how quickly baryonic matter can collect within these potential wells. Yet Webb has observed galaxies such as CEERS 93316, which exhibits a stellar mass exceeding 9 solar masses, implying that the host halo must have gathered enormous amounts of baryons in a fraction of the expected time. This discrepancy suggests that either halo formation proceeded faster than predicted, or additional mechanisms contributed to early mass accumulation. The challenge is compounded when considering halo abundance. LCDM simulations predict the number density of massive halos at Z is greater than 11 to be extremely low, on the order of 10, -5 per cubic megaparsec for halos above 10 solar masses. Webb surveys, particularly CEERS and GLASS, have identified multiple such massive systems in small fields, implying a far higher abundance than predicted. For example, GLASSZ121 exhibits both a high stellar mass and compact structure within a halo that, under standard models, should not exist at that redshift. The number and mass of these early galaxies appear inconsistent with the predicted halo mass function, highlighting a fundamental tension between observations and dark matter-based models. Baryon conversion efficiency further limits early galaxy growth. In simulations, only a fraction of baryons within a halo, typically 5–20%, are converted into stars due to feedback from supernovae, radiative pressure, and heating. To reach stellar masses of 9 solar masses in under 400 million years Halos would need to convert baryons at efficiencies approaching 50% or more, far exceeding standard predictions. This high efficiency is difficult to reconcile with LCDM, particularly given the observed presence of metals and dust, which indicate prior stellar generations and suggest feedback should have slowed subsequent star formation. Webb's findings, therefore, challenge assumptions about how baryons interact within dark matter halos. Halo merger rates also appear insufficient to explain rapid galaxy growth. Hierarchical models predict that mergers are a primary driver of early galaxy assembly, yet the timescales required for multiple mergers at Z is greater than 11 are tight. To assemble the observed stellar masses, progenitor halos must form, merge, and convert gas into stars within roughly 200–300 million years. This leaves little room for delays caused by dynamical friction, tidal stripping, or inefficient gas accretion. The extremely compact and organized structures observed in galaxies such as CERs 9, 3316, GLASS Z121, and SMACS JD1 indicate that these systems underwent accelerated assembly, challenging the conventional merger-driven halo growth picture. Dark matter halos are also expected to influence galaxy rotation and morphology. In standard models, the distribution of dark matter determines the rotation curves and the development of disks. Observations from Webb reveal early disk-like structures and bulges with relatively smooth rotation profiles at Z is greater than 11, suggesting that baryons settled into organized orbits very quickly. Such early disk formation requires both rapid baryonic collapse and a stable dark matter potential. Yet the predicted halos at these redshifts are often too low in mass and too irregular to support the observed structures. The presence of well-defined disks implies either unusually massive or concentrated dark matter halos, or alternative processes facilitating angular momentum redistribution. Chemical evolution adds another layer of complexity. Webb observations detect metals at abundances of 10–20% solar and significant dust content in galaxies at Z is greater than 11. Standard halo formation models suggest that early halos should host only minimal stellar populations, insufficient to produce the observed enrichment levels. The presence of heavy elements implies multiple generations of star formation, meaning baryons must have collapsed efficiently and repeatedly within dark matter halos. Given the expected inefficiencies in feedback-regulated star formation, standard dark matter halos alone cannot easily account for the observed maturity and chemical complexity. Further discrepancies emerge when examining large-scale structure and galaxy clustering. High redshift galaxies detected by Webb often appear in close proximity, forming proto-cluster regions far denser than predicted. For instance, the CEERs and glass fields contain several massive systems within a few hundred kiloparsecs of each other, implying that the underlying dark matter distribution is both denser and more clustered than LCDM models allow at Z is greater than 11. These proto-cluster environments enhance gas accretion rates and merger probabilities, but the density and rapid assembly still exceed what standard halo growth predicts, suggesting that dark matter alone is insufficient to explain these early formations. Alternative dark matter models, such as warm dark matter, have been proposed to address some tensions in halo formation, but they introduce additional problems. Warm dark matter suppresses the formation of small halos, reducing the number of progenitor structures available for mergers. While this could explain the lack of smaller galaxies in some surveys, it worsens the problem of early, massive galaxy assembly, as fewer halos are available to host the baryonic mass needed to build 10-9 solar mass galaxies in the first 400 million years. Observations from Webb indicate that the number of early massive galaxies is already higher than standard LCDM predicts, meaning that suppressing small-scale structure does not solve the discrepancy. High-velocity inflows of gas have been suggested as a mechanism to bypass dark matter limits, allowing baryons to accumulate faster than expected. Simulations indicate that cold streams along cosmic filaments can deliver several solar masses per year per kiloparsec into halos, sustaining rapid star formation. While these inflows may help explain the accelerated growth of individual galaxies, they still rely on the underlying dark matter halo to provide the gravitational potential. The observed stellar masses, chemical maturity, and structural organization imply inflow rates and efficiencies near or beyond the limits of current models, further indicating that dark matter alone cannot fully account for early galaxy formation. Another factor is the interaction between dark matter and baryons. In standard LCDM models, baryons experience pressure, cooling, and feedback, while dark matter is collisionless. Observations of early galaxies provide data on star formation rates, chemical enrichment, and disk formation, which can be compared to predictions of baryon behavior within collisionless dark matter halos. Galaxies observed by Webb provide measurements of stellar mass, stellar populations, chemical abundances, structural features, and clustering properties. These observational data can be used to evaluate the predictions of standard dark matter halos, including halo growth rates, baryon conversion efficiency, and merger histories. Comparisons of measured properties with LCDM models allow quantification of discrepancies and identification of areas where models may require adjustment. How Webb's data was independently verified. When the James Webb Space Telescope began producing deep infrared images of the distant universe, astronomers were immediately excited and cautious. Webb's discoveries have undergone some of the most rigorous observational checks ever applied in astronomy, combining multiple independent techniques to ensure that the signals interpreted as early galaxies are real, stable, and at the distances reported. One of the most fundamental verification methods is spectroscopy. While initial identifications of candidate high redshift galaxies rely on patterns in color and brightness across different infrared filters, spectroscopic measurements provide direct evidence of distance. Telescopes can spread the incoming light into a spectrum and identify specific features caused by hydrogen, oxygen, and other elements. This lets astronomers measure how much the wavelength of those features has stretched due to cosmic expansion, a quantity known as redshift. For example, a major survey specifically designed to probe the earliest galaxies used nearly 28 hours of spectroscopic exposure targeting a handful of promising candidates identified in deep JWST imaging. These observations verified that some of them have redshifts as high as 13.2 by clearly detecting the characteristic break in the spectrum caused by neutral hydrogen absorption at these distances. This break, known as the Lyman break, shifts into the infrared at such early epochs and is highly diagnostic of redshift when confirmed spectroscopically, rather than just inferred from broadband imaging. Another noteworthy spectroscopic confirmation came from extremely luminous early systems observed in deep fields. Two galaxies with exceptionally strong infrared fluxes were spectroscopically confirmed at redshifts around 14, placing them near or within the first 300 million years after the Big Bang. The spectra revealed broad ultraviolet continua with clear breaks and no strong emission lines attributed to active galactic nuclei, indicating that the light originates from large populations of young stars rather than an accreting supermassive black hole. These confirmations demonstrate that massive, well-populated galaxies existed far earlier than previously thought. Spectroscopic verification also plays a critical role in spotting and correcting misidentifications. In early deep images, one galaxy appeared to be at an extremely high redshift based purely on its colors. But follow-up spectroscopy showed that its redshift was much lower once specific emission lines were measured, which helped recalibrate how color breaks are interpreted. This kind of revision is an important part of the verification process because it prevents reliance on photometric estimates alone, which can be more prone to confusion with dust reddening or line-emitting galaxies at moderate redshift. Cross-observatory follow-ups add another layer of independent verification. Facilities such as the Atacama Large Millimeter, Submillimeter Array or ALMA have been used to detect far-infrared emission lines in some of the same fields targeted by JWST. For example, ALMA detected a strong signal from ionized oxygen atoms in a galaxy originally identified in Deep Space Telescope imaging, confirming its spectroscopically measured distance independent of Webb. ALMA's millimeter and submillimeter observations also help confirm that the galaxy's interstellar medium contains cool gas and dust consistent with early star formation. Ground-based telescopes equipped with sensitive infrared spectrographs also contribute to validation. In cases where Webb identifies spectral features, other observatories can attempt to confirm these features at complementary wavelengths or using different instruments. This multi-instrument approach reduces the likelihood that an observed spectral line is an artifact of a particular instrument or data reduction pipeline. The agreement between different telescopes' measurements gives high confidence that the redshifts and intrinsic properties assigned to these galaxies reflect reality. Verification also depends on rigorous instrument calibration. Webb's near-infrared instruments, including the near-infrared camera and spectrograph, operate at very cold temperatures to minimize thermal noise. Teams continuously calibrate detectors with observations of standard stars whose brightness and spectrum are well known, which enables accurate measurement of flux and color for faint galaxies at great distances. Calibration procedures also correct for pixel sensitivity variations, cosmic ray hits, and optical distortions. By repeatedly calibrating and cross-validating these corrections with multiple standard fields, scientists ensure that the measured brightness and spectral features are truly astronomical rather than instrumental. Data processed by Webb goes through independent reduction pipelines developed by separate teams. Each pipeline applies corrections for detector noise, background subtraction, cosmic ray removal, and flux extraction. Independent groups using different software and assumptions reduce the same raw data, and consistency between the final results increases confidence in the measurements. For example, spectroscopic features such as the Lyman break or ultraviolet continuum slope have been recovered reliably across reductions by different teams, which supports the robustness of the detection rather than a processing artifact. Large, deep field surveys also use statistical validation techniques to test whether the number and distribution of candidate galaxies are plausible. One common method involves inserting artificial sources with known brightness and redshift into raw imaging data, then running the same detection algorithms used for the real observations. Recovery rates from these tests indicate how reliably true galaxies would be detected at different brightness levels, and how often spurious noise features might be mistaken for real objects. In many early JWST deep fields, these tests show that galaxies at redshift Z is greater than 10, with magnitudes brighter than a certain threshold, are recovered with high efficiency, and false positives remain rare, reinforcing the significance of the real detections. When galaxies are observed behind massive foreground clusters, gravitational lensing corrections must be applied to infer intrinsic brightness and size. Foreground cluster gravity bends and amplifies the light of background galaxies, making them appear brighter and larger than they are intrinsically. Teams model the mass distribution of the foreground cluster using multiple observed lensed images and known physical constraints. Then apply this model to estimate the true luminosity and size of the background high redshift galaxy. Consistent results from different lensing models, including both parametric and non-parametric methods, enhance confidence in the corrected properties. Repeated observations help confirm that candidates are not transient objects or data anomalies. Galaxies identified in one epoch are often observed again months later in different filters or programs. Stable detection in the same position with consistent flux levels supports the interpretation that these are real galaxies, rather than transient events like supernovae. In several deep fields, high redshift candidates have been firmly detected in repeated visits spanning months, which eliminates transient explanations. International peer review and collaboration also contribute to verification. Webb's deep field datasets are public, and research teams across multiple countries independently analyze the same observations using different assumptions and methods. Debates about interpretation, such as whether light from a source is best explained by star formation or another mechanism, are resolved through additional spectroscopic observations and coordinated follow-ups. Publication in peer-reviewed journals requires rigorous checks by referees who evaluate the methodology, statistical significance, and plausibility of the data interpretation before acceptance. Finally, Webb's observational results are compared to theoretical simulations of the early universe. Large cosmological simulation projects generate synthetic populations of galaxies at different epochs, including redshifts, comparable to those Webb is probing. By inserting simulated galaxies into mock Webb observations and running them through the same detection and analysis pipelines, scientists test whether the patterns seen in real data, such as the distribution of brightness, size, and spectral breaks, align with physically plausible early galaxy populations. These simulation cross-checks do not prove that each individual galaxy is correct, but they help confirm that the overall detection strategy and interpretation procedures align with theoretical expectations under standard cosmological models. Verification methods include spectroscopy, repeated imaging, cross-observatory follow-ups, instrument calibration, independent data reductions, statistical testing, and comparison with simulations. Using these techniques, astronomers have confirmed galaxies with spectroscopic redshifts beyond 10, including some near redshift 14, based on multiple independent lines of observational evidence. Where cosmology simulations fail, early observations from the James Webb Space Telescope reveal massive galaxy systems in the universe's first few 100 million years. Prior to these observations, theoretical models based on the lambda cold dark matter framework used large computer simulations to forecast how structures form across cosmic time. These simulations describe large-scale structure and galaxy populations at moderate redshifts and provide predicted trends for the number, mass, and distribution of galaxies at earlier epochs. Cosmological simulations hinge on a few basic assumptions. They start with initial conditions measured from the cosmic microwave background, and then evolve dark matter, gas, and radiation forward under gravity and other forces. Early simulations like Millennium and Illustris used millions to billions of particles to model the formation of galaxies and clusters, predicting, for example, that small structures form first and merge over time into bigger ones. In these models, the number density of galaxies at a given mass and redshift follows a well-defined trend. At very high redshifts, galaxies should be both rarer and much smaller than at later epochs. Even more recent simulation suites, such as Illustris TNG, include sophisticated hydrodynamics and feedback processes and are calibrated against a broad range of observations at later cosmic times. Yet these state-of-the-art simulations still struggle to fully account for the early universe as Webb sees it. One of the most persistent discrepancies arises in predicted mass and luminosity functions for the earliest galaxies. Simulations generally forecast far fewer bright, massive galaxies at redshifts above 10 than Webb is detecting. When researchers use simulations to generate mock catalogues of high redshift galaxies and then process those datasets as if they were real telescope observations, the number of predicted galaxies meeting Webb's brightness and number density thresholds is significantly lower than what the telescope reports. In some cases, Webb finds nearly twice as many massive galaxies in deep survey fields than the models suggest should exist in comparable volumes of space. This disparity hints at shortcomings in how simulations model star formation efficiency and gas accretion at very early times. Another related mismatch emerges in galaxy evolution trends. Simulations predict that galaxies at very high redshift should be dominated by small, irregular systems with moderate star formation rates, gradually merging and growing over time. This hierarchical assembly is foundational for many models of cosmic structure formation. Yet Webb's deep imaging and spectroscopy reveal a surprisingly high fraction of galaxies with organized structure, significant stellar mass, and signs of sustained star formation well beyond the levels predicted for such early epochs. Some of these systems exhibit disk-like features and compact bulges that resemble more mature forms usually expected only at later times. These structural characteristics are challenging to reproduce in simulations that assume a slower, incremental growth process. Part of the difficulty lies in the resolution and physical modelling of current simulations. Simulations span a wide range of scales, from small, high-resolution boxes that can capture individual star-forming regions to enormous volumes that model galaxy cluster formation, but each choice involves trade-offs. High-resolution early universe runs, such as those from specialized projects, succeed at modeling initial star formation down to relatively small stellar masses, but only up to tens of millions of years after the Big Bang, and often only for smaller mass scales. Lower resolution cosmological boxes can simulate massive halos, but lack the detail to capture the internal processes that regulate rapid star formation. Without simultaneously resolving both the smallest star-forming regions and the largest cosmic structures, simulations struggle to reproduce the range of masses and luminosities Webb observes. Discrepancies also appear in the predicted efficiency of gas cooling and star formation. In simulated early galaxies, gas must cool efficiently to collapse and form stars, but feedback from early supernovae and radiation pressure pushes back against this collapse. In many models, these feedback processes reduce star formation efficiency at high redshift, limiting the mass that galaxies can build up by a given epoch. Webb's observations, however, suggest that many early galaxies were able to convert gas into stars much more efficiently, possibly because the physical conditions in the early universe, such as higher gas densities and lower metallicities, altered the balance between cooling and feedback. This could point to missing or oversimplified physics in current simulation codes, such as the treatment of molecular cooling, dust formation, or early radiation fields. The populations of black holes and active galactic nuclei, or AGNs, predicted by simulations, also differ from what Webb sometimes suggests. Observations of high redshift sources reveal signatures of rapid gas infall and high velocity gas near galaxy centers in some cases, hinting at the presence of growing black holes alongside intense star formation. Simulations based on LCDM generally predict that massive black hole seeds should take longer to grow into the supermassive engines powering AGNs. Yet Webb's detections include systems that appear to house rapidly growing black holes at very early times. Bridging this gap requires improvements in how simulations model the seeding and early growth of black holes, as well as their feedback effects on host galaxies. Efforts to reconcile simulations with Webb's findings have included adjusting key parameters and exploring alternative cosmological scenarios. Some studies have increased the assumed efficiency of early star formation or modified the initial mass function of stars to favour the rapid buildup of stellar mass. Others have investigated the effect of environmental overdensities, regions where matter was initially denser, which can accelerate structure formation in localised patches beyond what average cosmic models predict. These adjustments can bring simulation outputs closer to observed number counts and masses in some cases. But no single parameter tweak has yet produced a comprehensive match to all of Webb's high redshift findings. Researchers are also exploring high-resolution simulation suites designed specifically to model early galaxy formation with greater physical fidelity. These include projects that track individual star clusters and complex gas dynamical processes in tiny cosmic volumes, evolving from the first molecular clouds to starburst phases. Such simulations reveal that under certain conditions, early galaxies can grow rapidly, seeding their halos with significant stellar mass within a few 100 million years. However, current computational limits mean it is difficult to scale these detailed models up to the volumes needed to compare with deep sky surveys, leaving a gap between detailed physics and observable galaxy populations. Even when simulations successfully reproduce some aspects of early galaxies, they often fall short in explaining the full distribution of observed properties. For example, observed early galaxies appear more numerous, more massive, and more chemically enriched than predicted by many large simulations. These differences appear across multiple surveys and fields, suggesting they are not statistical flukes or observational biases, but fundamental issues in how current models describe early structure formation. Part of the problem lies in the baseline assumptions of many simulations, which were calibrated using observations of moderately distant and nearby galaxies. Extrapolating these calibrations to conditions at redshifts greater than 10 assumes that the same physical processes and scaling laws remain valid across huge changes in cosmic time and environment. Webb's observations suggest that reality may be more complex, that the early universe had physical conditions and processes that our models have not fully captured or parameterized. The mismatch between Webb's early universe observations and cosmological simulations does not necessarily mean that the standard cosmological framework is wrong, but it does highlight the need for refined simulations and new modeling strategies. Integrating more detailed physics at high resolution, improving feedback prescriptions, and expanding computational capabilities to model early galaxy growth across larger volumes are active areas of research. Future simulation efforts will be tested directly against Webb's expanding dataset, serving as an ongoing feedback loop between observation and theory. Current cosmological simulations do not fully reproduce many properties of early galaxies detected by JWST. Observations indicate that simulations need to incorporate additional physics, higher resolution, and updated assumptions regarding galaxy formation, growth, and interaction within the first billion years of cosmic history. What older than the Big Bang really means. When a galaxy observed by the James Webb Space Telescope is described as seeming older than the Big Bang, these results from the interaction of look-back time, redshift, and cosmic age at emission. Concepts like light travel time and stellar population ages must be considered within physical models of the universe to interpret these observations accurately. The starting point is recognizing that when we observe distant galaxies, we are looking at light that was emitted billions of years ago. Light travels at a finite speed, so when Webb detects a galaxy with a redshift of, say, 13, it means the photons left the galaxy when the universe was only a few 100 million years old. In that case, the light has been travelling for roughly 13.4 billion years before reaching our telescopes today. Because of cosmic expansion, the present proper distance to such a galaxy now may be more than 30 billion light-years. But the key measurement is the time when the light was emitted, not where the galaxy is now. Astronomers convert redshift to a look-back time, which is a measure of how far back in time we are seeing an object. A redshift of around 13 corresponds to light emitted approximately 330 million years after the universe began its expansion. That early epoch corresponds to just a few % of the universe's current age, commonly estimated from cosmological models at about 13.8 billion years. Because different cosmological models produce slightly different mappings between redshift and age, there is some inherent uncertainty, often a few % in these conversions. But the broad picture remains consistent. The universe in those early epochs was young compared to its present age. It is important to distinguish look-back time from absolute age of an object. When a galaxy is observed at high redshift, the look-back time tells us when the light was emitted, but the galaxy itself may have formed hundreds of millions of years before that emission. Stellar population modelling, which interprets a galaxy's spectral energy distribution to estimate the ages of its constituent stars, can indicate that much of a galaxy's stellar mass was in place before the light we see was emitted. In some high redshift systems, these models suggest the bulk of star formation may have started tens or even hundreds of millions of years earlier than the emitted light's timestamp. This can create apparent tension with cosmic age estimates when comparing stellar population ages and redshift-based emission ages. This tension between the inferred age of a galaxy's stars and the cosmic age at the epoch of emission is what sometimes gets described in oversimplified terms as an object being older than the universe. Strictly speaking, no galaxy can predate the cosmic age at the moment the light was emitted. The universe's timeline, under standard cosmological frameworks, always starts at a defined origin event, and every structure that formed did so after that origin. What can happen, however, is that stellar population models may produce age estimates that challenge assumptions built into cosmological models, or that reflect uncertainties in how early star formation proceeded. These discrepancies highlight two important points. First, the interpretation of stellar ages depends on physical models of how stars form and evolve over time. And second, cosmological age estimates depend on global parameters such as the present expansion rate and the densities of matter and dark energy. Because both of these areas involve complex physics and observational uncertainty, their intersection can produce results that appear in tension with simple narratives about cosmic age, rather than indicating a true violation of the cosmic timeline. These tensions signal areas where models may need refinement. One aspect that contributes to this complexity is the intrinsic uncertainty in converting redshift to cosmic age. The relation between redshift and age is not a simple linear mapping. It depends on how quickly the universe expanded as a function of time. Small differences in the assumed expansion history, such as slight variations in the values of cosmological parameters, can change the inferred age at a given redshift by several percent. When astronomers quote ages based on redshift, they are always doing so within the context of a model for the universe's expansion. These conversions are sufficiently precise for most purposes, but extreme cases near the limits of observational reach, such as redshifts above 12 or 14, bring those uncertainties into sharper focus. Another critical distinction is between cosmic age at emission and light travel time. When a galaxy at redshift 14 is observed, the light has been travelling for about 13.5 billion years. But this figure does not represent the current age of the galaxy itself. It represents how long the light took to reach us. In the time since that light was emitted, the galaxy has continued to evolve, and its present age in its own cosmic location is still older. However, that later evolution does not feed back into the interpretation of the light we see today. Webb's observations effectively freeze a moment in cosmic history, allowing astronomers to reconstruct conditions at that epoch. This interplay of look-back time and cosmic age helps explain why phrasing like older than the Big Bang can sound misleading. If one combines a look-back time with a stellar age estimate naively, the sum can sometimes appear to exceed the age of the universe at the time of emission under simple assumptions. In reality, these are two different measures. One is how long the light travelled, and the other is how long stars have been forming within the galaxy before that emission. They are both constrained by the underlying cosmic timeline that begins at the universe's origin. Another layer of nuance is the expansion of space itself, which complicates intuitive notions of distance and time. The universe's expansion stretches the wavelengths of light, producing redshift, but it also means the present distance of a high redshift galaxy is not what it was when the light was originally emitted. This expansion does not alter the relative timing of events, but it does affect how we interpret distances and ages when correlating observational data with cosmological timelines. Measurements of redshift and distances must therefore be understood within the mathematical framework of an expanding spacetime. Because of these complexities, astrophysicists increasingly rely on multi-parameter analyses rather than single numbers when interpreting the earliest galaxies. By combining redshift measurements, spectral features, stellar population models, chemical abundances, and kinematic data, researchers build a more nuanced picture of when galaxies formed and how their stars evolved. These multi-objective analyses allow for better constraints on the timeline of cosmic dawn, the epoch when the first stars and galaxies lit up the universe after the cosmic dark ages. Under this refined understanding, there is no contradiction in observing galaxies whose inferred stellar ages challenge simple cosmic age estimates. Instead, these observations push the boundaries of our models, revealing that star formation and galaxy assembly may have proceeded rapidly under physical conditions very different from those in the modern universe. These early systems formed, evolved, and enriched their surroundings on accelerated timescales, resulting in stellar populations that appear mature even when viewed at epochs only a few 100 million years after the universe began. Astronomers interpret Webb's high redshift discoveries using measurements of look-back time, stellar population ages, and cosmic age at emission. Galaxies observed at redshifts above 12, approaching 14, provide direct data on conditions in the early universe, including the timing of star formation and the development of stellar populations. By distinguishing look-back time, cosmic age at emission, and stellar population age, astronomers can maintain consistency with physical models of the universe. Expansion models now under review. As the James Webb Space Telescope continues to reveal surprisingly massive and mature galaxies at redshifts greater than 10, cosmologists are rethinking the standard picture of how the universe expands over time. The conventional model of cosmic expansion, based on the idea that the universe is dominated by matter in the past and dark energy in the present, has long been remarkably successful at explaining a wide range of observations. Yet persistent discrepancies between different measurements of the universe's expansion rate and the unexpected early assembly of galaxies have spurred scientists to explore potential revisions or extensions to this foundational framework. One of the most closely scrutinized challenges in modern cosmology is the Hubble tension. Two precise methods of measuring the universe's expansion rate today yield different results. Measurements of the cosmic microwave background, reflecting early universe conditions, extrapolate to an expansion rate of around 67 to 68 kilometers per second per megaparsec. Direct measurements using local distance indicators such as Cepheid variable stars and type Ia supernovae consistently yield higher values near 73 kNet s MPC. This discrepancy persists even as observational uncertainties have decreased. To address this tension and to better align cosmological theory with Webb's findings of abundant bright galaxies in the early universe, researchers have proposed models that modify or extend the standard expansion history. One of the most discussed alternatives involves adding a new form of energy to the early universe, often termed early dark energy. Unlike the dark energy that dominates cosmic expansion today, which is assumed to be constant in time, early dark energy would have contributed a significant fraction of the universe's total energy density at specific early epochs before rapidly diminishing. This brief injection of energy would alter the expansion rate at early times without leaving a large imprint on late-time acceleration, potentially helping reconcile the differing estimates of the Hubble constant and adjusting the timing available for early structure formation. Early dark energy models typically involve theoretical fields or exotic components that behave like dark energy only for a limited period, often around the time when the universe transitioned from being dominated by radiation to matter. During that window, the extra energy density would have increased the expansion rate, effectively reducing the sound horizon, the scale imprinted on the cosmic microwave background, and bringing certain early measures into better alignment with local measurements. The proposed contribution of early dark energy to the total energy budget at its peak is generally modest, perhaps around a few percent, but its effects on the expansion history can ripple through to influence inferred parameters such as the Hubble constant and the formation timeline of early galaxies. These models are still under active review and adjustment as more precise observational data become available. Another aspect under consideration is whether dark energy itself might not be truly constant over time. In the standard model, dark energy is treated as a fixed background component, often referred to as a cosmological constant. This constant energy density drives the current accelerated expansion of the universe. However, recent observational studies of large galaxy surveys, quasars, and distances across the cosmos hint that the influence of dark energy may be evolving slowly rather than remaining perfectly constant. Some analyses suggest that the strength of dark energy's effect could be weakening, implying that the acceleration of the universe's expansion might slow or even transition in behavior in the far future. If dark energy is indeed dynamic rather than constant, it would require revising how cosmological models describe the late stages of expansion and could influence how we interpret the growth of structures at all epochs. Alongside early dark energy and evolving dark energy scenarios, some researchers have explored whether the nature of matter and its distribution could play a role in the observed expansion discrepancies. For instance, alternative models consider the possibility that additional components beyond ordinary matter and cold dark matter existed in the early universe, such as relativistic species or fields that influenced expansion in subtle ways. Others investigate whether interactions between dark matter and dark energy might slightly alter the effective expansion rate over time. These approaches often increase the complexity of cosmological models, introducing new parameters that must be constrained by data, but they reflect the ongoing effort to find a unified explanation for multiple observational tensions. Cosmologists also revisit assumptions about how perturbations in the early universe grew into the large-scale structures observed today. The distribution of galaxies, clusters, and cosmic voids offers clues about the underlying expansion history and the interplay between gravity, matter, density, and dark energy. Adjustments in the way perturbations are modelled or in the initial conditions of the early universe can shift predictions for how quickly structures could form and how their abundances evolve over time. Because Webb's observations show an unexpectedly high abundance of luminous galaxies at early times, these structural considerations feed back into the broader discussion of expansion history and its precise mathematical description. In evaluating all these alternatives, scientists use multiple cosmological probes beyond Webb's galaxy catalogues. The cosmic microwave background, with its detailed temperature and polarization patterns, provides a snapshot of the early universe that is sensitive to the entire expansion history up to that point. Baryon acoustic oscillations, the imprint of sound waves in the early universe, act as a cosmic yardstick that helps relate distances at different times. Measurements of supernovae across a range of redshifts track how expansion changes over time, while galaxy clustering and weak gravitational lensing reveal how structures have grown under cosmic expansion. Any proposed revision to expansion models must fit all of these diverse datasets simultaneously, which constrains how different mechanisms can be incorporated. One significant factor that has emerged in recent research is that altering the early expansion history, as in early dark energy models, can have knock-on effects for structure formation and the cosmic web. For example, if expansion was slightly faster in early epochs, the formation of dark matter halos, the gravitational wells in which galaxies form, could be enhanced or shifted in timing. This could help explain why Webb's deep observations show massive galaxies at redshifts that were previously unexpected. By adjusting the expansion history at specific ranges of cosmic time, the number and distribution of collapsed structures can become more consistent with empirical data. Despite the appeal of these alternative expansion scenarios, they are not universally accepted or fully tested. Detailed comparisons with observations show that some proposed models alleviate one tension only to introduce another, such as discrepancies in the amplitude of matter fluctuations at certain scales. The work of theoretical teams often involves fine-tuning parameters to achieve consistency with multiple observational constraints, which underscores the challenge of deviating from the well-tested standard model without sacrificing predictive power. Observations from Webb, cosmic microwave background experiments, large-scale surveys, and distant studies have revealed limitations in the simplest expansion models. Proposed alternatives include early dark energy, evolving dark energy, modifications to dark matter physics, or combinations of these effects. These scenarios are under active evaluation against observational data. Future observations, including extended Webb surveys, next-generation telescopes, and multi-wavelength campaigns, will provide additional data to test alternative expansion scenarios. Detailed comparisons between model predictions and observational data can constrain which models best describe the universe's growth and the timing of structure formation. The growing list of early massive objects. From the moment the James Webb Space Telescope began its deep surveys of distant cosmic neighborhoods, astronomers noticed something remarkable. The early universe was not sparsely populated with simple, tiny star clusters as many models had predicted. Instead, Webb continually revealed a growing roster of massive, complex objects emerging surprisingly early in cosmic history, in some cases only a few 100 million years after the Big Bang. These discoveries are reshaping our understanding of how quickly structures could assemble, how star formation progressed, and how early galaxies evolved into the mature forms seen at later times. One of the galaxies in this sample is JADES GS-Z 14-0, located at a redshift of roughly 14.2, corresponding to light emitted when the universe was about 300 million years old. Deep imaging and spectroscopy by Webb confirmed its distance. Its measured brightness and size indicate significant star formation and mass accumulation at this early epoch. Following closely are other high redshift Lyman break galaxies, such as JADES GS-Z 13-0 and JADES GS-Z 13-1, both observed in the deep fields that Webb has targeted repeatedly. These galaxies, at redshifts around 13, existed when the universe was roughly 330 to 350 million years old. Their detection relied on precise measurements of light that has travelled for more than 13 billion years, with spectral features providing reliable distances and insights into their internal stellar populations. The very fact that these galaxies are present, luminous, and structured at such early times indicates that intense star-forming activity was already underway shortly after cosmic dawn. Another prominent early system is Uncova Z12, identified behind a massive foreground galaxy cluster where the bending of space-time magnified its light enough for Webb's instruments to detect and analyze it. This object's redshift of about 12.4 places it at an age of roughly 350 to 400 million years after the Big Bang, and its luminosity implies a substantial population of young stars. Observational campaigns like the ultradepth NIRSPEC and NIRCam observations before the epoch of reionization have targeted such gravitationally lensed fields precisely to uncover galaxies that would otherwise be too faint to see. Beyond individual record-breaking galaxies, teams have reported hundreds of early bright galaxy candidates based on advanced infrared imaging and color selection techniques. Large systematic studies using dropout filters and spectral energy distribution fitting have found objects that appear unusually luminous for their estimated redshifts, indicating a broad population of early massive systems. If spectroscopic follow-up confirms even a portion of these candidates, the number of known massive early galaxies could grow dramatically, stretching beyond simple predictions of hierarchical assembly in the first 500 million years of the universe. The diversity of these early massive objects is striking. Some appear as luminous, compact galaxies undergoing rapid star formation. Others show evidence of interactions and mergers that would have boosted their mass much faster than isolated star formation alone. A particularly dramatic example, observed in Webb data, displays a double nucleus, a sign that two galaxies recently collided, triggering an intense central starburst phase. In this system, star formation rates reach hundreds of solar masses per year, far exceeding the rate in typical galaxies in the local universe, highlighting the extreme physical conditions driving early galaxy growth. Chemical signatures in some of these early galaxies add further complexity. When very distant objects contain dust and heavier elements rather than just pristine hydrogen and helium, it implies that at least one generation of massive stars had already lived and died before the observed epoch. The dust in these galaxies absorbs and scatters shorter wavelength light, producing distinctive reddening that Webb can peer through thanks to its infrared sensitivity. The presence of dust and heavy elements at such early cosmic times reveals that early stellar populations quickly enriched their surroundings, challenging models that expected purely primordial conditions at these epochs. Starburst galaxies discovered by Webb also illuminate the broader context of early cosmic evolution. Surveys have identified populations of small, intense, star-forming galaxies at ages around 800 million years after the Big Bang, many of which are thought to have played significant roles in cosmic reionization, the era when the first light sources cleared the fog of neutral hydrogen that filled the young universe. These starburst systems, while less massive than the extreme objects at redshifts above 12, hint at a spectrum of early structures, ranging from tiny, numerous star factories to rare, massive galaxies whose assembly was surprisingly rapid. Gravitational lensing, the magnification of background objects by massive foreground clusters, has been a crucial tool for expanding the census of early massive objects. In several deep field projects, the bending of light by clusters like Abell 2744 has enhanced Webb's reach, allowing astronomers to detect galaxies at redshifts near or above 12 that would otherwise be too faint. This technique has revealed multiple instances of high redshift galaxies with significant stellar masses, confirming that the early universe hosted both abundant, low-mass systems and rarer, but still common enough, high-mass galaxies. Observations of early massive galaxies show a range of masses, luminosities, and structural features. Some galaxies accumulated mass through rapid star formation from dense gas inflows, while others underwent mergers within the first few 100 million years. These variations indicate multiple formation mechanisms active in the early universe. The observed abundance of massive early galaxies appears higher than predictions from simple hierarchical models that assume slow mass buildup. Data suggest rapid gas accretion, cooling, and starburst cycles contributed to early mass accumulation. The growing dataset of early massive galaxies allows testing of models for dark matter, halo formation, star formation feedback, and early chemical enrichment. Webb's ongoing deep field observations continue to identify additional high redshift galaxies. Each confirmed system provides data on the timing and properties of early galaxy formation. Future instruments, including the Nancy Grace Roman Space Telescope and next-generation ground-based observatories, will expand survey areas and provide complementary observations of these early structures. Observations of early massive objects indicate the presence of significant galaxy formation within the first few 100 million years after the Big Bang. Record-breaking galaxies and candidate high redshift systems provide data for studying the processes that shaped the formation and growth of large, early galaxies, which contribute to the structure of the present universe. Observations planned to resolve the conflict. As the James Webb Space Telescope continues to reshape our view of the early universe, astronomers are now preparing an ambitious lineup of future observations designed to resolve the mounting discrepancies between observation and theory. The unexpected abundance of massive galaxies at very high redshift, the tension between inferred cosmic expansion rates, and the surprising chemical complexity seen in early systems are not anomalies to ignore. They are the drivers of new experimental campaigns and coordinated surveys that aim to fill the gaps in our understanding. These planned observations go well beyond simply finding more distant galaxies. They are structured to probe the physical conditions, timing, and mechanics of cosmic dawn with precision across multiple wavelengths and instruments. One of the major avenues of inquiry involves high-precision spectroscopy on a large scale. Webb's NIRS-SPEC instrument has already enabled detailed spectral analysis of individual high-redshift galaxies, such as JADES GS-Z 13.1 and Uncova Z12, revealing information about their redshifts, ionized gas, and star formation activity. Building on these successes, astronomers are now designing deep spectroscopic surveys that will push beyond current redshift limits to systematically measure hundreds of early systems. These surveys plan to focus not only on redshift confirmation, but on detailed spectral line diagnostics, including hydrogen emission features like H-beta and Lyman alpha, and oxygen emission lines that trace ionization states and metallicity. By capturing a broad sample of emission lines, researchers hope to map out the star formation histories, gas conditions, and chemical enrichment pathways of galaxies forming as early as 200 and 5,300 million years after the Big Bang. To expand both depth and breadth, Webb's observing programs are increasingly combined into large legacy field surveys. One such initiative involves repeated deep imaging and spectroscopic mapping of fields with extensive coverage from multiple telescopes. By integrating data across surveys, astronomers can reduce uncertainties in photometric redshifts, improve signal-to-noise for faint spectral features, and create robust catalogues of early universe objects. These datasets support construction of detailed luminosity functions across a wide range of redshifts to characterize the population of massive early galaxies. Complementing Webb's deep but relatively narrow pencil beam views are wider field surveys planned with other observatories. Chief among these is the Nancy Grace Roman Space Telescope, equipped with a wide-field infrared camera that can scan much larger areas of sky than Webb at similar wavelengths. Roman surveys are designed to reach depths near 26-27 AB magnitude across much wider regions, enabling the discovery of hundreds to thousands of faint active galactic nuclei and early quasars at redshifts above 7. These objects will act as beacons of early black hole growth, shedding light on how supermassive black holes formed and grew alongside their host galaxies in the first billion years. Roman's multi-epoch observations will also allow for the study of variability in these early systems, which can be used to distinguish active nuclei from purely star-forming galaxies and to constrain black hole accretion histories. Ground-based facilities are also gearing up for coordinated follow-ups. Large telescopes, such as those in the extremely large telescope class, including the Giant Magellan Telescope and the 30-meter telescope, will bring high spectral resolution and adaptive optics imaging to bear on select Webb targets. With these instruments, astronomers can resolve detailed kinematics, how gas and stars are moving within early galaxies, and measure dynamical masses. This helps refine estimates of how much mass resides in stars versus dark matter halos, and whether early galaxies are rotating disks, mergers, or irregular systems. Resolving these dynamics is key to testing whether the rapid growth seen by Webb can be reconciled with the expected timescales for gravitational collapse and halo assembly in standard cosmological models. One of the most promising targeted observation plans involves deep gravitational lensing surveys. Massive galaxy clusters act as natural cosmic telescopes, magnifying background light from extremely distant galaxies that would otherwise be too faint to detect. Programs focusing on clusters like Abell, 2000, 744, and others identified in the Hubble frontier fields will continue to be observed repeatedly with Webb, exploiting lensing magnification to push the frontier of redshift sensitivity even further. These surveys are expected to reveal extremely faint galaxies at redshifts, possibly beyond 15, offering direct probes of the population of the earliest star-forming systems, and providing statistics on how many such galaxies exist at each epoch. Another set of planned observations focuses on the epoch of reionization, when the first galaxies and stars ionized intergalactic hydrogen. Galaxies such as JADES GSZ 13.1 show evidence of ionized regions. Future programs will map the distribution and sizes of ionized bubbles using multi-filter imaging and deep spectroscopy. By measuring changes in Lyman alpha emission with redshift and environment, astronomers can infer the timeline and distribution of ionized regions in the early universe. Observational campaigns are also being designed to measure chemical abundances in early galaxies with unprecedented precision. By detecting weak emission lines from elements such as nitrogen, oxygen, carbon, and neon, researchers can infer the degree of chemical enrichment and the relative contributions of different generations of stars. For instance, some galaxies may show nitrogen to oxygen ratios or carbon abundances, indicating multiple cycles of star formation within a relatively short cosmic interval. These chemical fingerprints provide insights into the initial mass function of early stars, whether they were mostly massive stars or had a broader mass distribution, and how quickly heavy elements were synthesized and distributed within the first galactic systems. In tandem with these direct observations, astronomers are planning time domain studies, repeated observations of the same deep fields at multiple epochs to catch transient events such as supernovae in the early universe. Detecting supernovae at high redshift provides information about the life cycles of the earliest stars, the rate at which massive stars died, and the influence of these explosive deaths on the surrounding medium. Early supernova surveys with Webb have hinted at a population of exploding stars in the first few billion years, and future programs aim to quantify how common these events were, how they influenced early galaxy evolution, and how they contributed to metal enrichment on cosmic scales. These observational strategies aim to combine Webb's infrared deep field data with wide field surveys from next-generation telescopes like Raman, high-resolution ground-based spectroscopy, and gravitational lensing magnification. This approach will provide measurements of galaxy properties and allow investigation of how dark matter and dark energy influenced early structure formation. In the coming decade, these planned observations aim to measure the abundance of massive galaxies at redshifts above 10, determine processes driving rapid star and black hole assembly, and characterize how the intergalactic medium transitioned from neutral to ionized. These data will help reduce uncertainties in physical models of early galaxy formation and evolution. How these findings are changing cosmology. The discoveries made by the James Webb Space Telescope are not just expanding the catalogue of distant galaxies, they are fundamentally reshaping the field of cosmology. By pushing observational frontiers deeper into cosmic history than ever before, Webb has revealed that the early universe may have been far more dynamic, efficient at forming structures, and chemically complex than many theoretical frameworks had predicted. These observations are forcing cosmologists to rethink long-standing assumptions about how the universe grew, why certain patterns exist in the distribution of galaxies today, and how fundamental processes like star formation, black hole growth, and cosmic reionization unfolded in the first billion years. One of the most striking impacts of Webb's early universe findings is the growing recognition that star formation efficiency in nascent galaxies may be much higher than previously thought. In the decades prior to Webb's launch, models of galaxy formation generally suggested that early star formation was slow and limited by the availability of cool gas. Recent analyses of ultraviolet luminosity, functions at redshifts above 8, which represent how the brightness of galaxies evolves over time, indicate that the efficiency with which gas turned into stars in early halos might have been significantly greater than in later cosmic epochs. This suggests that the first generations of galaxies were highly effective at converting their gas into stars, possibly due to higher gas densities and more rapid cooling mechanisms present in the infant universe. The concept of rapid chemical enrichment is also being observed. Previously, it was assumed that early galaxies would be dominated by pristine hydrogen and helium, with heavier elements appearing only later. Webb's spectral observations of certain high redshift systems show signatures of heavier elements such as oxygen and nitrogen at early epochs. For example, unusually high nitrogen relative to oxygen has been detected in a galaxy containing extremely massive primordial stars, which are believed to have lived for a few 100,000 years before collapsing into black holes. The timeline of cosmic reionization, when the first stars and galaxies ionized neutral hydrogen, is being updated with Webb's data. Prior estimates placed the end of reionization at around 900 million years after the Big Bang. But measurements of the intergalactic medium's transparency around galaxies show that large bubbles of ionized gas had already grown and merged by this time. Webb's instruments have mapped these transparent zones, which often extend millions of light years from the galaxies responsible for ionization. Black hole formation and early growth are being investigated using Webb observations. Several early universe galaxies show active galactic nuclei at high redshift, powered by supermassive black holes accreting gas. The presence of such black holes, less than 1 billion years after the Big Bang, suggests rapid growth. Hypotheses include direct collapse of massive early stars or rapid accretion in dense environments, which are being incorporated into models of early black hole formation. Protoclusters, groups of galaxies assembling into larger structures, have been observed at relatively early epochs. Protoclusters at redshifts below 10 contain multiple galaxies bound by common dark matter halos moving at high velocities relative to one another. These observations indicate that gravitational clustering occurred within a few 100 million years after the Big Bang. Webb observations provide data relevant to the influence of dark matter and dark energy on early cosmic evolution. Dark matter's gravitational effects are inferred from galaxy distributions and dynamics. The presence of massive early galaxies and protoclusters indicates that dark matter halos may have grown larger and more quickly than predicted by some simulations. Analyses of galaxy clustering and surveys suggest that dark energy's influence may have changed over time. In response to Webb's disruptive data, theoretical cosmology is undergoing a period of vigorous revision and innovation. Instead of treating the standard model of cosmology as an unshakable foundation, researchers are actively exploring extensions and alternatives that can accommodate both Webb's early universe observations and well-tested phenomena, such as the cosmic microwave background and baryon acoustic oscillations. Some proposals involve modifying assumptions about star formation thresholds, initial mass functions of stellar populations, or the efficiency of gas cooling in small halos. Others entertain more radical changes to the physics of the early universe, including additional relativistic components or interactions that enhance early structure growth without conflicting with established constraints. These theoretical explorations are tightly linked to increasingly sophisticated simulations. New simulation campaigns are incorporating Webb's empirical data including updated ultraviolet luminosity functions and high redshift galaxy populations, to produce more realistic models of early cosmic evolution. These simulations aim to reproduce the abundance, luminosity, and structural features of galaxies seen at redshifts above 10, while maintaining consistency with the observed properties of the universe at later epochs. Some approaches are also examining how alternative dark matter properties or interactions could influence early halo growth, potentially bridging the gap between theory and observation. Observationally, Webb's discoveries influence survey design for future missions. Upcoming telescopes, such as the Nancy Grace Roman Space Telescope and next-generation ground-based observatories, are planned with capabilities to address specific gaps highlighted by Webb. Roman's wide-field infrared imaging will complement Webb's deep but narrow surveys, enabling statistical studies of galaxy populations across large cosmic volumes. Webb's deep-field observations and detailed spectroscopy provide constraints on parameters such as star formation efficiency, galaxy merger rates, chemical enrichment timelines, and ionization histories. These empirical inputs are being incorporated into updated cosmic evolution models. In the years ahead, the conversation between observation and theory will only deepen. Webb's ongoing surveys are likely to reveal even earlier and more distant galaxies, probing epochs that lie closer to the actual onset of structure formation. These discoveries, combined with advanced simulations and complementary data from other observatories, will continue to test the boundaries of current models and potentially lay the groundwork for entirely new paradigms. What was once theoretical speculation about the early universe is now grounded in observational reality, and each new finding continues to revise and enrich our understanding of how the cosmos came to be.